Hello and welcome to this new course or new series of aircraft science. This is the second part of aircraft series. The first one was about all the systems and instruments of an aircraft, studying these instruments and how do they work. This series is about troubleshooting and emergency procedures. Now, perhaps the word or the naming series is not as accurate. This would be like a full video, and then it would be broken down to different chapters that you can separately watch as well. At first, as a disclaimer, the content of this presentation is mainly informative and should not in any way be used to replace the official documents, the official aircraft operation manuals and guidelines. Okay, so it's more informative, but it's not an official guideline for the procedures that should be employed during emergency and during troubleshooting of an aircraft, neither in the ground operations. Module 1 or Chapter 1, Fundamentals of Aircraft Troubleshooting. What is troubleshooting in aviation? Troubleshooting in aviation is the systematic process of identifying, that's first, analyzing, and correcting or rectifying abnormal behavior in aircraft systems, such as hydraulic system, electronic, electrical, monitoring, alarms, etc., while maintaining flight safety. And unlike general problem solving, aviation troubleshooting must account for the following. Time pressure, which means that you have a very limited amount of time or a lapse of time in which you can act before things start breaking down and the situation start escalating. Okay, so you have a limited lapse or amount of time or a short interval. Second, limited information, which means that you need to follow a checklist. You have limited amount of information that you can go by in order to rectify the problem. More than that, and this rarely happens, in few cases where nothing else to be done within the checklist, you need to improvise, but do it precariously and thoughtfully so as to not fall into a situation where the problem escalates and it becomes more toxic, it becomes more dangerous for the flight safety. You have also a high workload environment, so you need to act quickly while maintaining focus, plus with lesser amount of trials and errors, which means you have severe consequences of incorrect decisions, which might, and it had during the past, brought down airplanes and made the situation even worse. So you need to account for the severe consequences of incorrect choices, incorrect decisions, and incorrect assessment and analysis of the problem that you have at hand. From a pilot's perspective, troubleshooting focuses on interpreting cockpit indications and warnings, such as the master caution and other notifications and indications on the screens, such as the ECAM, which stands for Electronic Centralized Aircraft Monitor, and the ECAS or Engine Indication and Crew Alert System, which displays the performance of the engines, the N1 and 2 rotation in modern aircraft, which stand for, and large aircraft, which stand for the RPM, revolution per minute, of the lower pressure compressor on the outside of the engine and the higher pressure compressor. Also, you have the oil pressure, the EGT or exhaust gas temperature, and with all, not only the measurement, but the red highlighting when there's a problem, the abnormalities indicated on the screen, and other types of warnings. And then, okay, after that, you identify the affected system, whether the engine, the controls, etc. Then applying correct procedures, which are memory items or checklists, or following the guidelines within the aircraft manual. From a systems perspective, troubleshooting relies on understanding normal system operations so that you can understand or identify abnormalities, failure modes, so as to see when the system is failing, and redundancies and protections, which means that you have systems that can exist with multiple backups, and you need to rely on these backups when the original instrument had failed. Now, aviation troubleshooting is therefore both a technical and a cognitive process requiring disciplined thinking, okay, a trained mindset, a trained thought, and also internalization, if I may add, okay, which helps you think and operate under stress. Internalization is like after a while, when you start learning how to drive your car, after a while, you become so, it becomes a second nature to you, so as to, you start operating without even thinking. You know that when something happens, you need to push the brakes, you need to do this or that. Okay, this is what internalization is. You no longer think because there's no much time on the aircraft during the flight to think and analyze and try to assess a problem for a long time. You need to act swiftly. Abnormal, non-normal, and emergency situations. Okay, aircraft operational deviations are commonly classified into three categories. So, any deviation from normal operation is classified into three categories. You have abnormal situations at first. Abnormal situations are system malfunctions that do not pose immediate danger, okay, but they can escalate. We need to assess them. Allow sufficient time for diagnosis, so you would have enough time to assess the problem. Typically require checklist action, so you need to go into your checklist in order to rectify and assess and analyze what's happening. Examples would include alternator failure with battery remaining. So you have an alternator that had failed. The alternator is the one that generate alternative power, okay? And once it fails and you still have battery remaining, you need to go into the checklist to see how dangerous the problem is, because you might lose a control in such case. Minor instrument discrepancies. So, for example, the attitude indicator might be acting up and not displaying accurate indications. So, you need to rely on a backup, for instance. And finally, fuel imbalance. Second case, non-normal situations. Non-normal is a broader term often used in modern aircraft documentation, such as the ECAS or ECAM. Again, ECAS stands for Engine Indication and Crew Alert System, and ECAM, Electronic Centralized Aircraft Monitor, to describe any deviation from normal operation, including both abnormal and emergency conditions. It emphasizes procedural compliance rather than severity. Okay, so it emphasizes to comply with the procedure, with like a specific checklist in order to make sure that the engines are operating based on the protocol, based on the way they should be operating, without any deviation, from the normal, even if that deviation or that infraction, despite the fact that it's violating the protocol, even if it's not so dangerous, it needs to be rectified. It needs to be fixed. So it emphasizes procedural compliance rather than severity. It emphasizes to comply with the procedures, with the norms, rather than, the severity of a condition. 3. Emergency situations. Emergency situations involve an immediate threat to aircraft controllability, structural integrity, so some things or some controls or some parts of the airplane might be prone to break apart or might have started to break apart, such as the landing gear housing cover or cap. Occupant survival, so let's say a drop of oxygen after a decompression, that would be an emergency situation that would require landing, immediate landing. Characteristics include immediate action required. Immediately or swiftly, you need to act upon the problem to mitigate the effect. Memory items often apply, such as the checklist and minimal diagnosis before action. You need to immediately identify the problem before acting up. You need to immediately go in the checklist and try to pick up exactly what had happened, because you have a short span of time in order to act before the problem becomes more severe, before the problems become more dangerous, endangering the entire flight. Examples: engine fire or engine backfire, rapid decompression, which what we've mentioned moments ago, such as you have a puncture in the airframe and a release of the pressured air from the inside to the outside, or a complete engine failure or flame out right after takeoff, which won't give you enough time in order to act. By the way, it happened in the famous Hudson River landing where both engines flamed out during a takeoff. This happened in New York City, in Manhattan, I think. So right after takeoff, 4 or 6 giant birds slammed into the engines, which caused the engines to roll back. Both of them. Both of them flamed out. And the pilot had to land immediately, and he had no time and no marge of distance to fly back to the airport, so he had to land on the Hudson River. And miraculously, yeah, it was all God that did that. I completely believe it. Everyone survived this landing, which was a ditch on water, basically. The decision-making loop. Effective troubleshooting follows a continuous decision-making cycle, which starts from detecting, like seeing or spotting the indication or the alarm and detecting the problem, then diagnosis, then decision making. After decision making, you take action. After that, you need to review if the decision that you made had given the hope or the expected results, and was it effective, or worse than that, was it a mistake to go in that direction? Okay, so you need at first to detect, diagnose the problem, decide on it, or like decide by taking an action, doing that action, and then reviewing the action that was taken. Detection occurs through warning systems, different alerts, master caution, for example, lights, auto alerts, which means you would hear a beep. For example, in the stall warning, you would hear, for smaller aircrafts, a noise, a whistle, which is a sounder or like a horn connected to an inlet that detects when the air is no longer flowing normally but upward, and that air would go through the inlet to activate the whistle horn, indicating a stall for the pilot. Or you have, I think it's both in larger aircrafts and smaller aircrafts, the stick shaker warning, which also indicates a stall. You have instrument indications, for example, indications and notifications and warnings on the computer monitors. Example, the ECAM and the ECAS. Also, aircraft behavior or performance changes. For example, the controls seem to be sluggish. So that would be an indicator that the aircraft is not operating normally anymore. There's a sluggishness, okay? There's a laziness in the controls. Early detection prevents escalation of failures, which can make a bad situation worse. This is why it's very important and needed. Diagnose. Diagnosis involves identifying at first the affected system. So which part of the aircraft has been affected by this fault, whether the hydraulics, the engines, the electronics, electrical, and let's say if it's the engines, which part of the engine, and how to go about it. Then cross-checking multiple indications to verify that the problem is truly what is indicated. For example, if I'm going into a climb and there's something wrong, okay? So the airspeed is increasing. I need to check the altimeter to make sure that the altitude should be increasing during a climb. Also, the VSI, vertical speed indicator, should be also positive, indicating a positive rate. You need to also look at the attitude indicator. So am I pitched up or down? If the altitude is not increasing, the VSI is leveled and the airspeed is increasing, it means that there might be something wrong with the elevators, for example. Finally, eliminating false or secondary symptoms, which means isolating the fault and understanding that the secondary faults are a result of the first one. Just like when you have a power cut in your house, all the systems would go off. Like the TV would be turned off, the refrigerator, all of the other things. But the root problem is none of the other systems that are connected to the power, but it is the power itself. And incorrect diagnosis is a major contributor to accident chains. This is why diagnosis should be done precariously, very effectively, very cautiously, and in focus, so as to avoid having more escalating problems. And because since a misdiagnosis can lead to more serious, dangerous problems. Third, decide. Decision making requires assessing severity, how severe the problem is, and urgency. Choosing between continuation of the flight or diversion to the closest airport, or termination of flight, correct? Exactly. Termination of flight, it can be the abortion of takeoff when the aircraft is still on the runway and it's still below V1, meaning that the takeoff speed, or like not the takeoff speed, V2 is the takeoff speed. However, V1 is the decision velocity or airspeed. Once you go over that, you can no longer abort the takeoff because you wouldn't have enough runway, enough distance to make the aircraft halt and stop. So you would need to take the entire problems or failures airborne and fix the problem while you're in the air. So before V1, any problem should be spotted so that you can abort the flight before you take off, which makes it even more serious. Now, third, here within the decision making, selecting the appropriate procedure to take. Do. This phase includes executing memory items and checklists. Memory items meaning the things that you have trained on and you've memorized. These are in your mind. These are prompt actions that you take whenever something occurs based on the type of indication or problem that you've encountered. For example, I think it was Qantas flight. I don't remember which number it was. Flying from, I don't know, from New Zealand to Sydney, something like that. I don't remember. Okay. And I don't remember the flight plan. But what happened is that in mid-flight, one of the engines exploded, creating a backfire. The moment that happened, the pilot immediately pressed the altitude hold button, okay, which meant the aircraft level and nose down so that it can become more stabilized as the crew started to work on the problem. Second, performing checklist actions, so going into a checklist. And third, communicating with the air traffic controller or ATC and communicating among the crew in order to help solve the problem, and with the ATC in order to, alert the ground over the problem that you're having. And in case there's an emergency, you want for the ATC to clear your airspace so that you can land immediately, or descend to a lower altitude so that you can fix or start troubleshooting the problem. The last stage is review. Review ensures that the situation is stabilized after you've performed the checklist and you had made the decision and taken the appropriate, hopefully appropriate action. No new failures have occurred because we need to assess, okay, did it work or has something else developed during that same time? And the chosen strategy remains valid. We should assess if the chosen strategy had remained valid and has it rectified the problem and mitigated, you know, the situation that had developed. Finally, the loop repeats as conditions evolve. By the way, we can call this process the 4DR if you want to memorize it. So 4DR, which stands for detect, diagnose, decide, do, and finally review. Okay? 5 steps. So again, detect, diagnose, decide, decision making, do, and finally review what has been done. Priorities of action: aviate, navigate, and then communicate. These are the priorities in order. At first, you have a problem, you need to continue flying the airplane, then navigation, okay, orienting the airplane, navigating, and communicating with the ground so as to receive directions and vectors for landing, for instance. Okay, so aviate, navigate, communicate. Aviate, which means maintaining aircraft control, is the top priority when something happens. Pitch, the bank, the power of the aircraft, the airspeed control, aircraft configuration. No checklist or communication is relevant if control is lost, the control of the aircraft. Navigate. Once control is assured, once the pilot had taken control of the aircraft and stabilized it, then comes navigation. What it means is determining aircraft position or heading, avoiding terrain, which is low altitude or like hitting the ground. This is what terrain means. And weather conditions, severe weather conditions, like you should not find yourself in the midst of a storm. Third, select suitable airports or landing areas. In case of airports are not available in proximity, you need to go for the closest area where you have a flat land in order to land the aircraft, or ditching at the sea at the worst case scenarios. Okay. Then communicate. Only after aviation and navigation, you need to declare the urgency or emergency, request assistance from the ground, coordinate with ATC. At times, the assistance can be requested from an aircraft engineer on the ground, coordinating with the air traffic controller, and this hierarchy prevents distraction-induced loss of control. Time critical versus time available failures. Okay, time critical failures. These are the failures, the types of failures that require immediate action, prompt action, and allow little to no diagnosis. So they need to be acted upon promptly, which includes engine fire, smoke in the cockpit that can be, a lurking fire in the undercarriage that had the smoke going all the way up to the cockpit, or like a fire in the electrical systems, something had overheated in one of the instruments or the electrical cables, or an electrical surge. Multiple possibilities that are, can lead to a fire, or this can be a developing fire on board. Third, stall or loss of control. Stall is when the aircraft can no longer produce lift, or a loss of control. For example, it happened multiple times. A rudder hard over. It broke and went sideways and jammed. Okay, the rudder jammed on one of the sides, either to the left or to the right. Characteristics: you have memory items need to apply in such case. So whatever you have in your own memory as a trained pilot, in case you are a pilot, you need to go there immediately and do what needs to be done. For example, in some cases, disengaging the autopilot because it can be relying on wrong readings in order to navigate or to fly the aircraft. Then you have actions before analysis, okay? Taking action like taking the control before starting the analysis, and high risk of rapid escalation, okay? So you have, in such case, high risk of problems escalating and becoming more dangerous than what you already have going on in the cockpit as an indication. Time available failures. Time available failures permit diagnosis and checklist use. For example, you have generator failure, like the turbine within the engine, pressurization anomalies. For example, it surge in the atmosphere within the cabin, or a leak of the air on the outside due to a puncture in the airframe or something like that. Navigation system failures, so whether you have an interference or a glitch in the navigation systems, the ILS, etc. Or, for example, the directional gyro is giving wrong directions, wrong headings for one reason or another. It had broken. Characteristics, analytical troubleshooting, so you still have time to repair in such case. Crew coordination, coordinating between different parts of the crew, the co-pilot or the flight engineer in some cases, and strategic planning. Understanding the difference between these two categories is essential in order to avoid delayed action in critical situations or rushed decisions that can lead to even more major problems when time is available. Module 2 or Chapter 2, Human Factors in Emergencies. This includes stress, startle effect, which means when the pilot, due to a sudden event, would react swiftly, okay, like it would catch him by surprise and he would do an inappropriate action in order to fix the problem, okay? But he would be reacting in a very wrong way. For example, during a stall, because it had caught him by action, instead of pulling or pushing down the nose so that the aircraft would gain more airspeed, in order to recover from the stall, he would be pulling the yoke backwards, which would increase the aircraft's AOA or angle of attack, making the stall even worse. Third, you have tunnel vision. Another word for that would be target fixation, which means that you are only focused on one indicator, one instrument, while disregarding other things that are occurring in the aircraft. Okay, so you become so obsessed with that one erroneous indication while forgetting to observe and monitor other indicators, other instruments, which is very vital in order to troubleshoot the problem. Let's start with the stress in aviation emergencies. So, stress is a physiological and psychological response to perceived threat or high workload. Okay, so when you have a high workload or perceived threat, something that seems to be threatening to the aircraft, you would feel yourself or you would find yourself under so much stress that it can alter your sound judgment on how to react to the problem. In aviation emergencies, stress directly affects reaction time. So you might find yourself dumbfounded and lost and missing in action instead of jumping promptly to the procedure checklist. Cognitive processing, so you would have a wrong assessment of the situation. You fail to process what's happening and to understand exactly the situation and to perceive like the exact problem within this, or like to perceive what's exactly going on what are the things that have been affected during an emergency. Also, motor coordination, which is coordination between your mind and your hands. So, reacting correctly on the controls, which I mentioned earlier when by giving the example on like the stall warning and the pilot reacting oppositely to what is appropriate. So instead of pushing forward on the yoke, pushing backwards, creating more stall. And finally, decision making quality would also be affected and altered under stress because it would be more emotional instead of logical. Okay? So the reaction wouldn't be sound, wouldn't be correct. Stress is more dangerous. This is why pilots need to be overly trained, okay, in order to rectify and in order to be able to cope under stress and execute the normal, you know, protocols and procedures that are already in the manuals. Performance under stress follows the Yerkes-Dodson law, which states that performance increases with arousal up to an optimal point, but beyond that point, it deteriorates again. So, stress is optimal for awareness up to a certain point, but beyond that, it becomes detrimental to focus and to correct decision making. So, where performance P and A is the arousal or the stress level. So the performance is a function of the arousal, but it's not linear, so to speak. Excessive stress shifts attention from analytical thinking to instinctive reactions. So it becomes like a primal instinct working and making decisions instead of your own analytical thinking and logic, which increases the risk of procedural errors. Startle effect. The startle effect is an involuntary physiological reaction to a sudden, unexpected stimulus. For example, a loud bang, loud warning, abrupt aircraft motion, such as a sudden lurch due to a rudder hard over, a loss of control. Okay, this effect or the effect of this will include the following: temporary cognitive paralysis, which is up to 3 seconds, loss of procedural recall, so you wouldn't be able to recall from your memory what are the prompt actions to be taken in such case, delayed or inappropriate control inputs, so you would act inappropriately with the controls in order to swiftly correct the situation, but you can be doing the exact opposite of what should be done. Startle reduces available cognitive capacity. So available cognitive capacity is equal to total capacity minus the cognitive capacity during the startle that has been taken away. Okay, minus the reduction of the cognitive capacity due to a startle event. This reduction explains delayed responses in sudden emergencies such as engine failure after takeoff. Tunnel vision. Tunnel vision is attentional narrowing caused by high stress, where focus would be restricted to only a single item or a single cue or a single warning, while other critical information, which is lying or scattered around other instruments within the aircraft, within the cockpit, would be completely ignored. Examples, and again, this is also called target fixation. So, fixation on one instrument is part of the tunnel vision, not necessarily all of that. Being fixated on an engine indication or the attitude indicator. Second, ignoring or like a fuel measurement, which had happened was one of the pilots once, and he ran out of fuel. Actually, he wasn't fixated on the fuel level, but on a minor engine problem or indication, I believe. Then, ignoring airspeed while troubleshooting, which is very important because you can get into a stall, and because of your focusing on something else, you would like miss being within the stall and not reacting properly when that happens. Also, missing ATC calls or warnings to divert or to take like a prompt action to climb, etc. Tunnel vision increases the probability of error by reducing cross-checking between different instruments so as to verify what's happening and to assess correctly the problem. Situational awareness loss. SA or situational awareness is defined as the pilot's understanding of the perception of elements in the environment, okay? So whether he is perceiving correctly the readings of the instruments, comprehension of their meaning, so what is happening with the aircraft, what is its attitude, its airspeed, whether it's climbing or diving based on these readings, based on the output of the aircraft instruments, whether through monitors or through classical instruments on board. Projection, third, projection of their future status. So projecting on what would be the behavior of the aircraft based on these readings, whether you're about to get into a stall or to lose controls, okay, all of that. Now, levels of situational awareness. Level 1 is perception, which is noticing relevant data that's being presented in front of you and exactly the things that you need the most for your current situation. Second, comprehension, understanding what this data means, okay, and how they can tell you on whether you're flying leveled, you're climbing, what's your attitude, what's your airspeed, level the flight or not, your heading. Level 3 is projection, so anticipating a problem before it happens. A more common example is before entering a stall, you would see some warnings such as a large angle of attack, a low airspeed, etc. Loss of SA or situational awareness typically occurs when workload exceeds cognitive capacity. So W would be the task workload. When it's greater than C, which is the cognitive capacity, you would have a loss of SA or situational awareness. SA loss often precedes controlled flight into terrain or CFIT and unstable approaches when it comes to fixing or dealing with the problem. Another note here to mention concerning the CFIT, although it may sound to be something positive, it's not. It means literally flying into the ground, okay? So controlled flight into terrain, meaning that the pilot is not aware that he's actually approaching the ground, the terrain, and he would fly his airplane into the ground without even noticing what happened. Or when he notices what's happening, it would be too late. This is what CFIT means. Workload management. Definition of workload. Workload is a total mental and physical effort required to perform all the tasks at hand during a given amount of time. So W is given by the sum from I equal 1 to N, which is the number of tasks, of Ti, which is the individual task demand, okay? And of course, is the number of concurrent tasks that are occurring or are required to be performed almost simultaneously at the same time. Overload and underload. Overload, which means too many tasks in a limited time should be accomplished, which can put enough stress on the pilot and the crew. And underload is the exact opposite when you have too few tasks leading to complacency, meaning that, the pilot would become so relaxed, overly relaxed, that he would lose his edge when it comes to flying the airplane, especially due to the increase of the amount of automation in modern day aircrafts. Okay, both conditions degrade performance, by the way, and situational awareness. Workload reduction strategies. This, or like the effective workload management, includes prioritization, which is the sequence of aviating, navigating, then communicating, okay, sequentially, of course. Second, automation management, management of automation and guiding the autopilot into the tasks that he needs to do and managing what are the different inputs that should be like sequentially added to the autopilot to enhance the performance of navigation. Task shedding, which means that the tasks that are not a priority, they should be relinquished into another time, or they can be delayed basically. Four, crew coordination and delegation. Delegation means that when the pilot needs to take some rest, he needs to delegate the operation of the aircraft to the co-pilot or vice versa by saying these three words: you have control, and the autopilot would take control of the airplane. Also, he needs to reply back to him, I have control, which means that the aircraft is in my hands now. Error chains and threat and error management, TEM. Okay, so error chains. What is an error chain? It is a sequence of interconnected events or mistakes, and that when they are not broken, when this sequence remains unbroken, it can actually lead to an accident. So, the probability of an accident, an aviation accident basically, is equal to the sum of the probabilities of different events occurring one after the other that would actually lead to a crash eventually. So, each probability would contribute, or the probability for each connected event added up one after the other would contribute into leading to a fatal crash. So PEI is the probability of individual error events. So one misdiagnosis leading to one inappropriate action, leading to another inappropriate action. All of that accumulate in order to form a scenario or a perfect atmosphere for a disaster, basically. Now, breaking any link in the chain can interrupt this accident or can interrupt the sequence of events so as to avoid the accident even taking place, which is very important. So, reviewing the checklist, reviewing the misapproaches, not misapproach when it comes to the landing, the missed handlings of the problem would help you avoid or avert a more dangerous situation. Now, TEM or threat and error management. TEM is a proactive safety framework that recognizes the following: threats, which are the external events increasing the risks; errors, like mishandlings of or wrong actions taken by the crew, or even inactions. So the crew might be MIA or missing in action due to the traumatic event that had taken place, or like a severe lurch in the aircraft, a severe hard over in the rudder, something malfunctioning that sent the aircraft into the jolt, into a jolt. This can affect the performance and the awareness of the crew, okay, and leads them to commit errors. Also, undesired aircraft states or UAS. The TEM flow is threat, error, and UAS or undesired aircraft states, which leads to an unfavorable outcome. Effective TEM relies on detection, mitigation, and recovery. Checklist discipline versus memory items. So let's start with memory items, which are the immediate actions performed without going back to a reference checklist, okay, without going back to a checklist. These are the immediate actions to be taken by a pilot, and it would be like a reflex reaction, okay, a reflex act without going back into analysis and troubleshooting. These should be in precedence when you have an emergency on board. So the characteristics are time critical, because there's a less tolerance in wasting time in such case. For example, when you have a problem with the rudder, you should take the controls immediately. At times, you are required to immediately disengage the autopilot or the auto throttle when you have a rollback, for example, on the engines due to a wrong flare off activation by the aircraft. And it happened before where the aircraft was placed in a retard mode while rolling back the engines to idle because of an erroneous reading of the altimeter. Okay, so the altimeter read -8, which means that the aircraft was already on the ground. And since the autopilot is performing its decisions based on the readings of that altimeter instrument, this caused the crash. So characteristics are time critical, limited in number, so you have 1 to 3 steps that should be immediately taken place, okay, and trained to automaticity, which means that it should be automatic reflex and right away actions that should be made. Examples include engine fire or stall recovery. For example, in engine fire, you need to extinguish the fire by, at first, you need to set the engine to idle and then, click the extinguishing button. Checklist discipline. Checklists provide structured verification of different steps that need to be taken. Error trapping, meaning that you mitigate the probability for errors when you follow a specific standard, which gets us to the third point, which is standardization, meaning that you go into one step after the other, which has been verified by the test pilots and the aircraft designers before you in order to narrow down the window, in order to mitigate the errors, especially during a narrow window of reaction, okay, based on the type of problem or emergencies that you're having on board. Now, we need to take into account that at times, especially when you have something that requires an immediate action, you need to go by memory, which was the previous step, before going into the checklist to troubleshoot the problem. Because when you have a loss of control, for example, or an engine fire, you should go immediately into pulling down the levers or the throttle, okay, back to idle, and then extinguish the fire, okay? Because there might be a much narrower window of time and you have a grave emergency before the fire can spread into other parts of the aircraft. So the checklist usage reduces omission errors, so the probability of errors with checklists would be much lesser than that without checklists. Balancing between the two, which is between the memory items and the checklist. Now, over-reliance on memory increases error probability, especially when you're going into a sequence of steps within your mind, recalling back from your memory. And for example, you had flown more than one type of aircraft. So one action would be proper for one type of the aircraft without being proper for another type. It would be also improper or inappropriate for another types of aircraft. For example, someone who had flown all his years Airbus planes, and then he wants to transfer into Boeing. You see, Airbus is more automated. It doesn't rely as much on the the pilot's ways of dealing with stuff. Okay, so it's more automated because it has been the mindset that with more automation you have less pilot error. This has been the Airbus mindset. Meanwhile, Boeing has the mindset that the pilot is necessary in case the computers go rogue. He can fix the problem by retrieving the manual override. Okay, so but at the same time, okay, while you have error probability increasing because of over reliance on memory, premature checklists used during time critical events can delay actions, which can delay fixing the problem and leading to a more serious damage or more serious situation that would be developing, okay, that can render the aircraft irrecoverable at times. Like, for example, the aircraft banking to one side, like to the right, okay, there's a narrow window of time in which you can react before it can become irrecoverable and going into a tailspin. So the correct practice would be perform memory items, that's first, then stabilize the situation, okay, leveling the plane, the attitude, etc., and gain some stability after gaining control, of course. Finally, you transition into the checklist in order to verify different steps and to troubleshoot the problem, okay, and to rectify it all at once. This balance is essential for effective emergency management. Summary: human factors are often the decisive element in aviation emergencies. So you have technical failures alone rarely cause accidents. It is the interaction between system malfunctions or failures and human performance which is limited. So these limitations are what determine the outcome of an emergency. Understanding stress effects, workload, which is the number of tasks that should be executed simultaneously during an emergency, for example, error chains, and procedural discipline enables pilots to manage emergencies effectively and break accident chains before they can lead to an irreversible outcome. Chapter 3 or Module 3, Warning, Caution, and Indication Systems. All right. So, what is the purpose for warning, for caution, and indication? Warning, caution, and indication systems are designed to, first, alert the flight crew to abnormal conditions developing in the aircraft, prioritize pilot attention to the critical events that are happening above the secondary problems, and third, support correct and timely decision making, okay? Support correct and timely decision making by providing a checklist on board through the ECAM, for example. These systems do not replace pilot judgment, but they are an assistance. Instead, they act as decision support tools under high workload environments or conditions. Now, the alert hierarchy is generally defined as warning, which is the most critical type of indication, which requires an immediate action, okay, to respond or in response to an immediate threat to safety, like fire on board or engine fire. Second, caution, which is a potential or an indication to a potential threat requiring timely action, less critical than the warning, of course. And third, you have advisory / indication, which is an awareness information that you have, for example, the cabin is too cold, for example, an overly low temperature or an overly high temperature in one of the equipment, for instance. Visual, oral, and tactile warnings. Tactile means they are tangible, they can be touched, okay, they are sensed by the sense of touch. Let's start with the visual warnings. These are the visual alerts displayed on different indicators or on the screens, the centralized screens, such as the ECAM and the ECAS. This includes red and amber lights for like a very serious warning, text messages on displays, annunciator panel indications, like the ECAM and the ECAS again. The color coding follows standardized conventions. So, red, it requires immediate action that needs to be taken, like red alert, for example. Amber, awareness and timely action. So, it is serious also, but you have more time to react for an amber type of indication. And green, white, this is normal indication or advisory, okay? Like an indication for the N1 power of the engine would be green in normal conditions. Visual warning effectiveness depends on visibility and attention allocation. In other words, when something needs to be indicated, it should be visual and very clear to the eyes, plus, okay, not only the visibility, but the attention allocation, so it should not distract the pilot. It should be close to other instruments that need to be cross-checked during that alert being fired on that display screen. Auto warnings. Now, auto warnings provide attention capture regardless of pilot visual focus, which is very important because at times you need to grab the pilot's attention. He would not be looking at that moment at the indicator. So this auto warning would grab his attention even when he's visually distracted or looking at something else or busy running another type of procedures on the aircraft. Like they used to be busy running the calculation and the number for the remaining fuel, for instance. Okay, they would be distracted from, the crew would be distracted from looking at the visualizers, the screens. Examples: stall warning, you would hear it, okay, and it would beep. Pull up, that would be also like heard clearly, okay, the pull up procedure. Fire bell or chime, like you would hear the fire bell when you have engine fire or something like that. And auto alerts reduce detection time way less than the visual alerts, okay? So time for auto reaction is much less than that for visual reaction, because what you hear, it would grab your attention even much faster than what is visual. Tactile warnings. Tactile cues include stick shaker, stick pusher, so the stick would push automatically, and control column vibration, which is very important to indicate a stall, because these warnings bypass cognitive processing, which requires more time and latency so that the pilot can assess what's happening, and they act directly on motor sensors, on your own tactile sensors, which are the senses of touch. Particularly, they are effective during high-stress situations when you need immediate reaction to a specific kind of problem, such as the stall, okay? You wouldn't be aware of the stall in some cases unless there was a more violent sense or like a trigger that would override other senses such as the audible and the visual. You need something that is motory sensor so that you would react immediately to recover the aircraft from a stall, and these are mainly for a stall warning. Master caution and master warning logic. Master warning system indicates condition requiring immediate crew attention and action. So the activation logic can be expressed as follows. MW, or master warning activation, is equal to VWI, which means if one of these conditions has been met, okay, if one of these conditions is true, then the master warning indication would fire. So what are the WEs? So from 1 to N, these are the individual warning conditions. Okay, master warning indications are typically red lights, auto alerts, meaning audible, and flashing indications. So they would be flashing on and off to grab the crew's attention. Master caution system, similarly to the master warning system, the master caution alerts the crew to abnormal conditions. However, they are not immediately life-threatening, so you would have more time to react. But the same concept here, the master caution activation is done, or it fires off, when one among all the required individual caution conditions have been met. So if one of them, or it's enough for one of them to be true so that the master caution would fire. Okay, so CJ is an individual caution condition that is indexed from 1 to M. So you have multiple or M individual caution conditions. If one of them is true, if one of them, or it's enough for one of them to check out, then the master caution would fire off. Resetting the master caution does not remove the underlying fault. It only acknowledges the alert and removes the nuisance, okay, like the bothering sound from being, overly heard and distracting the pilots from doing their job and troubleshooting the problem. Alert inhibition and prioritization. To prevent nuisance alerts during critical phases of flight that can distract the crew, logic inhibits some warnings. Okay, so now A enabled, which means whether an alert has been enabled or not, is equal to 0. So it would be inhibited during takeoff or landing inhibition. Okay, that would be an inhibition. Okay, and 1, which means that the alert would fire on during other phases of flight, which is very necessary. So the alert would be kind of turned off during takeoff and landing. Okay, it would be inhibited so that it won't take the attention of the crew away from, controlling the aircraft in a critical phase in flight, during flight, whether the takeoff or the landing. Okay, or it would be 1, so it would be sounded or notified otherwise. This ensures only the most critical alerts are presented. False warnings and nuisance alerts. Let's start with false warnings. A false warning occurs when an alert is generated without an actual system failure behind it. So it's a warning, but it's not true, it's not accurate. It's not reflecting a real event happening at the same time, which should be translated correctly. So it's translating something that had not actually happened. So it's making it look like you have a fire, an engine failure, a loss of control, whatever the situation would be, without the actual problem taking place. Causes include, for instance, sensor malfunction. Now the sensors, let's talk about the thermal sensor, which reads, actually it's not itself that reads, but the computer system the computer system would be connected to an electronic card that senses the current coming from the thermal resistor. The thermal sensor RDS is a resistor that has its own current changing based on the temperature, the ambient temperature it is detecting. Why? Because its own structure is made in a way that you have a conducting material. When you have a low temperature around it, okay, that material would be stitched together. So it would allow the maximum current to go through it, acting as a short circuit. The RDS would be, okay, the thermal sensor would be. Meanwhile, if you had an overheat or a high temperature rise, this conductive material would stretch due to dilation, so the molecules would be separated from each other, reducing the conductivity of the current within the sensor, so which would be translated into a low current and analyzed or interpreted by the card, the electronic card, as an overheat or a fire even. Okay? Now, in case that sensor, okay, that thermal sensor snapped for whatever reason, like it broke, it would become an open circuit, allowing no current at all to be going through it. Meanwhile, you didn't have a fire. You have no fire on board, but the sensor itself had broken. But this would be translated by the electronic board, by the computer systems, as a fire on board, not even an overheat. You have a fire. Why? Because it snaps all together. Okay? Like the current, it did not even get too low. It became 0. So this would immediately be translated or interpreted as fire on board, although there is no fire at all. Another type of alarms would be the electrical noise. Okay, types or alarms would be going off due to electrical noise and interference being affecting the instrument itself and firing a wrong or a false alarm for something that had not actually happened. For example, another example is a short circuit. Like when you have a short circuit on the alarm system itself, it would indicate something that's not actually happening, okay? Or an open circuit, depending on the type of the sensor, whether it's normally closed or normally opens, which means if it's normally closed, in normal operation, the current would be going through it. When there's no current, it would be an alarm signal, or normally open, which means that when you have an alarm, the circuit would be closed in that moment, allowing the current to pass through it. Also, logical errors. For example, you'd have um, wrong processing of something that would lead to an error in assessment. Okay, you have logical circuits involved. This can be going in different directions here. So the false warning probability can be expressed as probability of false warnings is equal to 1 minus the probability of the sensor times the probability of the logic being wrong. Okay, so probability of false warning would be 1 minus probability of sensor being right, times probability of the logic. Okay, when these are completely wrong, one by one, that would give you, you know, 0 by 0, correct? So the probability of sensor being right times probability of logic being right, 0. So probability of false would be 100%. Nuisance alerts. Nuisance alerts are valid alerts that occur, however, at inappropriate times when the crew is already overtaxed with other jobs within the aircraft, within the cockpit to be more specific, and these alerts would start firing out of place and without an operational relevance. So, in other words, they would be identifying secondary issues while other things are more important to be focused upon during the flight and during that phase of the flight. The effects include alert fatigue, so the crew would be worn out from these alerts reoccurring and being recurrent due to their own nature. Plus, they would lead to delayed pilot response because they are out of place and the pilot is already busy being focused on something completely different. Third, distracted attention, so they would confuse the pilot. They would take away his focus, his attention, due to their bothering nature. Okay, so they present a very serious element of distraction. So the repeated nuisance mathematically, okay, the nuisance alerts reduce responsive effectiveness. So R, or the repeated nuisance, would be directly proportional to the inverse of the number of alerts being reported. So as the number of alerts increases, the effective response would be reduced, would be decayed. Okay, so you see it is inversely proportional here, where R is the pilot response quality. Annunciator panels and ECAM, ECAS philosophy. Again, ECAM is electronic centralized aircraft monitor and ECAS is engine indication and crew alert system. Traditional annunciator panels, older aircraft use discrete annunciator lights grouped by system, but should have them scattered on multiple locations on the on the display of the aircraft. So the characteristics are they are pilot-driven diagnoses, so you would need to go cross-check them by moving from one instrument to another. Higher cognitive workload, so you need, like it requires, it's taxing when it comes to cognition and assessment for the mind, to the brain of the pilot, because he would need to cross-check multiple instruments while trying to assess what's happening by monitoring multiple things, multiple indications at the same time. And these indications, these systems or instruments are scattered throughout the cockpit. Okay, so which would require a high attention span and a high focus, which also drives a higher cognitive workload to the scene. Third, greater reliance on memory and checklists. So you would need more reliance on the memory items and the checklist in order to try to assess a problem and interpret a fault. Okay, which has been fixed and mitigated to a high extent by the centralized aircraft monitors and the centralized display that can take different readings from different instruments, combine them, and integrate them in one display screen. ECAM and ECAS systems. Modern aircraft use integrated alerting systems such as the ECAM, or Electronic Centralized Aircraft Monitor, and the ECAS, Engine Indication and Crew Alert System. We've already mentioned that. These systems provide automatic fault prioritization. Okay, so this is based on a display for the most prominent and the most serious faults to be displayed. Checklist presentation, so it represents for you a checklist to go through it. On screen, which is very important. System synoptic displays, so alert prioritization follows logic. The priority is a function of severity of the fault and the phase of the flight that you're going into. And the philosophy differences, so for the ECAM, it emphasizes action guidance. Okay, it's based on action and it guides your action. But the ECAS emphasizes crew decision authority. Okay, so it gives authority to the decision, the crew-based decisions. Okay, both aim to reduce workload and error probability. Sensor failures versus real system failures. Okay, sensor-based alerting. Most alerts originate from sensors measuring data, like sensor for the pressure, for the temperature, for position, and for flow. An alert is triggered when a parameter exceeds a limit. So when you have x being measured is less than the minimum value acceptable, x min, or x exceeding a maximum value that would be acceptable, such as the temperature overheat threshold. Okay, so once you exceed that, that would be regarded as engine overheat. Actually, when you are within that margin, such as the X max and X mean would not necessarily be called temperature indication. Okay, X mean is the first, once you, for X less than X mean, it would be regarded as, for example, in the freezing, conditions. Okay, in the icing conditions. But you also have an interval that once you start crossing that interval, it would be indicated as an overheat of the engine. Okay, and between this first value, this threshold, and the second threshold, it would be acceptable. Once you trespass the second threshold, it would be regarded as, for example, engine fire. Okay, I hope it has been clear. Now, when we're talking about, okay, these two here, these two criteria, so X less than X mean, it would mean like, for example, when you are below the minimum pressure, it would be problem with hydraulics, for example, here, if the sensor is about hydraulics, or if it is, for example, when it comes to temperature, when you exceed a specific threshold, it would be regarded as overheat. And then after that, after a more critical value is crossed, it would be regarded or interpreted as engine fire. Let's talk a little bit more about the types of sensors and how do they actually work. When we talk about the pressure sensor, the most common one on the aircraft is the pitot-static system, where you have a ram air, that is the air from the outside running into the pitot tube, and it would be pushing against the static air that has been locked on the inside, okay, of this diaphragm-like compartment, okay, that was, by the way, stored while the aircraft was on the ground. This same air, okay, would be compared to the ram air that is pushing against it, and this push would be registering as the airspeed. More than that, you would have, for example, the altimeter and the VSI. We won't go into deeper details because they were already explained in the first part. So for the altimeter, you have the static air, that is the reference air, okay, that was stored back when the aircraft was still on the ground, on the runway. It is stored and locked within a diaphragm. This diaphragm will start dilating as the pressure difference grows between the air that is locked, that was stored on the ground, and, as you know, as we rise in altitude, the density of the air on the outside and the pressure, of course, as a result, would be decreasing. So the difference between the air from the ground and the external air pressure would increase, which will move a needle rotating to indicate more altitude as the aircraft climbs, because as the aircraft climbs more higher from the ground, okay, the differential between the pressure that is locked and the external pressure would grow. So this would cause a more turn, like a larger extent of turn within the altimeter, indicating more altitude. Now, for the VSI, it's a little bit tricky because it measures how fast the diaphragm is extending and contracting, and this contraction and extension, this is what actually would move the needle to indicate a positive or negative VSI, a positive attitude or a negative attitude. But this type of diaphragm in the VSI would returns back to its original shape once the climb has been conducted, and once the aircraft levels off, the diaphragm would restore or would retain its original shape, its original form and dimension. So basically, this diaphragm would only budge and move based on the change of the pressure, and it would dilate momentarily or contract momentarily, then it would regain its original shape, so as to indicate only the transition from one altitude to another that would reflect within the VSI as positive and negative rates, instead of indicating a specific value that would be fixed, like a specific altitude, as long as the aircraft remains on that altitude. For the temperature sensor, we've already explained that. So you have a sensor that is based on a resistor that would change its own resistivity based on the temperature on the outside. So for overheating conditions, it would dilate and block more current from getting through. That would be interpreted by the computer by reading, of course, the current at the electronic card. It would be interpreted as an overheat or high temperature or even fire when the current becomes zero. Meanwhile, for colder temperatures, that would be a normal operation, which means that the temperatures are nominal and enough current is passing through it so as to keep the conditions nominal, or like the notification conditions as normal without the need to fire a warning. Position, we're talking here about the directional gyro and the heading, which relies on both the compass and a rotating gyro in the vertical plane so as to stabilize the heading, okay? And finally, flow, which is a type of sensor that would measure actually, the moving fluid back and forth by detecting the pressure against or measuring like through rotation. You would have a wheel that would rotate based on the flow that's moving. This is how you can measure the amount of flow based on the rotation speed on this detection wheel. It would be like by the way, a river mill, okay, that is rotating and it's being, driven by the water flow. So the same concept can apply here. You have other sensors for the flow also that can measure the flow amount, or the density, not the density of the flow speed based on vibration of a probe that would vibrate through, as the fluid passes against it and move it. Sensor failure characteristics. Okay, sensor failures may produce the following. First, erratic indications. So you would have values or indications or numbers and measurements that don't make any sense, that are completely disconnected from the reality of what's happening. That's first. Second, conflicting alerts, and it happened before. For example, they had in one of the flights a pitot-static tube that was blocked due to a type of insect that was, that formed its own web within the pitot-static tube, partially blocking it. This indicated, it started detecting an overspeed in a high altitude, while what was really happening was a stall, which was indicated also by a stick shaker, a violent stick shaker. By the way, that's how you get conflicting indication, because the stall detection device is completely separate, is a separate device from the one measuring the airspeed, which is the pitot-static system. Okay, so the device for stall warnings would be the angle of attack detection and basically, yeah, the one, the stall switch that would be activated when the airflow is going upward on the wing instead of going around the wing. So that would activate the switch, which is a clear indication that the wings are no longer generating lift. So what happened with that aircraft is that meanwhile the airspeed was indicating an overspeed, actually a stall was happening that was a clear tactile warning, which is a stick shaker. This leads us to the third point, which is the implausible values, which means that you're getting values that don't make any sense. For example, an overspeed indication, meanwhile, you're within a stall warning at the same time. Doesn't make any sense. And by the way, the interpretation on why they had an overspeed, because you see, the air would be thinner on high altitude, so it would go through with a higher dynamic pressure within the pitot tube on higher altitudes, activating an overspeed alarm. Why? Because it would be read as if a high speed, okay? It would be rushing much faster within the pitot tube on higher altitudes because the thin air, okay, or the low density would be, manifesting as a thinner air going through the pitot-static system. So it would run much faster. Meanwhile, on the ground, they had a lower speed indication. Because the air is thicker, it would have a harder time to go into the pitot-static tube, and it would be detected as low airspeed on the ground. Redundancy reduces misinterpretation. So when you have multiple factors in play that need to be validated, okay, the validation would be more correct and accurate over the situation that is happening, which means when you are cross-examining and cross-referencing multiple instruments at the same time, it would be much safer and it would give you a more valid interpretation of the situation that's happening, reducing pilot error. This means that x validated is equal to 1 over n, the number of validation factors, sigma xn. So we're talking here about the average, okay, of the validation. So let's say for each system you have a validation of 0.5, which is 50%, or 60%. Let's say it is a percentage, okay? So the average percentage of validation for different factors, okay, should be greater than 0.5, average probability, so to speak, so as to designate the problem as being valid. To give you like a small application or example, let's say you have three factors. You have the attitude indicator, okay, VSI and altimeter. So the first one has checked out to be 0.6. It has an error of 0.6. The VSI is 0.4. And the altimeter is 0. Let's say 4 also. Let's check. Okay. So you have the average probability for error. Okay, average like probability if there's an error or not among these three would be the sum of these three probabilities divided by 3, because we have 3 indicators, right? So it would be 0.6 plus 0.4 plus 0.4. So divided by 3, which is 1 plus 0.4, 1.4 divided by 3. Okay, that would be, you have, okay, if we multiply by 10, you have 3.5, 15. Okay, so 0.5 won't work. 3.4, 12, okay, which would give you 2 here. Then 20 divided by 3, that would be 6. Okay, 18. Okay, so 0.466. This is less than 0.5. So it would be considered a false alarm, not a real failure, because it's less then 50%, which is the minimum required so as to validate a failure as a real failure, not a sensor glitch among different instruments. Discriminating real failures. So how to discriminate or to differentiate real failures? This is done by first cross-checking independent systems so as to get to a convergence. Convergence means that you are crossing or checking between multiple independent instruments and systems. And when you're arriving to the same conclusion, it means that the false alarm is real. You are on the right track of identifying a real problem taking place. Just like an investigation. When you go into a crime investigation using different threads, different directions, they need to meet or to converge at the same point, which will validate your research, which will validate your decision making and your discovery. All right? So when we go through different directions and yet get to the same conclusion, it means that this problem is validated. Second, observing aircraft performance. So we need to observe whether the aircraft is performing well, how it is performing, how the alarm is affecting the entire behavior of the aircraft. It might be, for example, when it comes to hydraulic problems, it would affect the controls. Then comparing redundant sensors. So when you have redundant sensors, and again, going back to that example where they had the pitot-static system blocked, partially due to a kind of bug that formed its web on the inside, okay, you need to cross-check it with another sensor. So if one was blocked, you need to rely on the second one. So let's say you have a stick shaker warning and it doesn't make any sense. Check the other instrument, the other ASI, airspeed indicator, connected to the second pitot tube to the right of the aircraft, where we have a completely different indication and everything is going okay. Okay? And the speed matches the stall warning or the lack thereof. So understanding alert system logic prevents incorrect actions triggered by misleading indications. Finally, warning, caution, and indication systems are essential safety tools, very necessary, but they are only as effective as the crew's understanding of their logic and how they intertwine with each other, and limitations as well. False alerts, sensor failures, and alert overload can degrade safety and affect the crew performance, by the way, if not properly managed. Effective pilots treat alerts as cues for analysis, not automatic commands, while respecting system prioritization and procedural guidance. Chapter or Module 4, Engine Malfunction and Failures. Engine roughness. Okay, let's start at first with the first case, engine roughness and partial power loss. Usually, engine roughness is due to the lack of oil. Imagine it or try to picture your own car engine, okay? When you have a roughness in the sound of the engine, it means that it is not turning properly against its own, its own gears, its own different pieces on the inside, like the crankshaft and other pieces. So when you have that kind of roughness, it means, or it indicates too much friction between different engine parts, which is leading to that sound that you're hearing, okay? This is usually due to the lack of oil and lubrication. And as for the partial power loss, that would be due, for example, to a rotating blade having been broken and other kinds of problems such as fuel starvation, for instance, okay? Not too much fuel being fed to the engine. So, definition and symptoms. Engine roughness and partial power loss refer to degraded engine performance without a complete failure, so the engines are still running. Typical symptoms include engine vibration. So the engine would start vibrating. This is one of the cues because it's not operating, it's not running properly and smoothly. RPM or torque fluctuations. RPM is the number of revolutions per minute. Also, EPR or engine power in some types of the airplane, like the MD-80 would indicate an EPR down. Okay, RPM again is the revolution per minute or torque fluctuations, also indicated in modern aircraft as N1 and 2 rotations. Loss of thrust, which is pushing the airplane, and it can be experienced as loss of lift on board, and abnormal EGT temperatures. Okay, EGT stands again for exhaust gas temperature. These malfunctions often allow continued operation, but they will deteriorate rapidly if not managed correctly. Let us right now try to delve deeper into the realm of physics in order to assess and interpret the reasons behind engine vibration and other types of symptoms being presented here without any prior requirement for an experience or understanding in the aircrafts. Okay, this can be obtained purely by physics analysis. Okay, by analyzing the physics of the engines and what would be happening on the inside or the outside when you would have any of these symptoms taking place. Let's start with the engine vibration. Now, mind you that any object performing a rotation around a central axis, okay, regardless of whether it is an aircraft engine or an automotive engine, but of course, it definitely applies to those as well. But to make it even more simple, any object rotating around an axis, okay, if this object is not uniformly distributed in weight around that axis, it would start causing vibration against the axis. That would be lateral, okay? A lateral force 90 degrees, away from the direction of the axis. So this force would be 90 degrees away. It would be pushing the axis laterally, and it would be back and forth motion. Why? Because this force that is not symmetric, it would be moving due to the rotation. So on one lapse of time or in half cycle, it would be on one side. Then after the half cycle is completed of the entire rotation, it would be on the other side. Think of it just like the PlayStation. If any of you had, deconstructed, or like he had taken apart the joystick or the handle of the PlayStation, you would notice that you have something that is a quarter of a disc, weight being on one side of an axis, not on all sides, which is on purpose to cause the vibration effect that you would feel in your hands when you are playing. So this was done on purpose. A weight, like multiple metal plates, have been placed on that axis, and they are only on one side in order so that when they rotate, they would cause the vibration of the joystick. This is the same concept in place here. Now, what would be the main reason when it comes to an engine for an aircraft? That would be a blade breaking off. So one of the blades would be torn off, which would cause, first of all, the weight being misplaced within the engine, plus that weight would be hitting other blades, and the disruptive airflow, the airflow that becomes disrupted due to that, it would no longer be flowing smoothly, would also increase the vibration rate, okay, and would affect other parameters such as the thrust and other things as well. When it comes to engine aircraft, this is what would happen. So you would have, for example, one of the blades breaking off, and this blade would at first disrupt the airflow within the engine. This is another reason for the vibration, but also it would be, that blade that had separated, more than disrupting the normal airflow within the engine, the weight had become imbalanced on the inside. So it is one side more weightier than the other side. Okay, so the aircraft would start shuddering, or like the engine would start vibrating due to that. It can be multiple blades breaking off at the same time. Not to mention also another result or it would be dire consequences at times because it usually leads to engine backfire. Why? Because due to the disruption of the airflow on the inside of the engine, so the fuel would not be fully combusted, okay? So it would start an engine backfire, which means that the combustion of the fuel is not complete due to the starvation or the partial blockage of the airflow. Second, RPM or torque fluctuations. Also, it can be due to something breaking within the engine, so it would no longer be running properly, or the RPM might fluctuate due to a suffocation, like a partial flame out of the engine due to starvation from oxygen, or the oil system is not, yeah, actually, it can translate into a dip in the oil pressure. Okay, so it would not be working properly. The engine would be stuttering. It can be an early indication of a low fuel gauge. Okay, so you need to open the cross feed, or like the fuel has been exhausted, so it would start fluctuating until it run out completely, usually due to oil starvation. Now, when it comes to RPM, also another scenario would be N1 and 2 rotations being affected in a larger aircraft due to damage within the engine itself. Also, as a result, it can lead to loss of pressure, especially when we've spoken about a rate, a you know a rate of rotation decreasing. Okay, that would lead to loss of pressure. Definitely, they are interconnected. Plus, if it was caused by a blade broken off, okay, breaking off during mid-flight, that would disrupt the airflow and it would lead to engine backfire, also with a partial loss of thrust. Now, another indication would be the abnormal exhaust gas temperature, or EGT indication. So the EGT would be overheated, for example, indicating an engine backfire, or it would be very low, indicating a rollback. These malfunctions often allow continued operation but may deteriorate rapidly if not managed correctly, as mentioned before. Common causes: first, fuel air mixture imbalance, which means that the fuel would be more excessive than the air itself, causing an improper combustion and leading to engine backfire, for instance, or front fire. This actually happens in one of the incidents in Florida where the aircraft became very overweight, so it pitched up during flight. And even before the crash, what happened was, because it pitched upwards abnormally, the angle of attack, the exceedingly large angle of attack, starved the engines from the normal airflow that was needed in order to have a proper fuel combustion, which led to an engine fire. It was like an engine front fire, I believe. Okay, why? Because the fuel was not being burned properly due to the lack of oxygen, which was caused by the abnormal or excessive angle of attack. Ignition system malfunction, for example, a problem or a defect in the sparking plugs, especially in the turboprop aircraft types, or magnetos. Induction icing or blockage, so blockage due to icing, for instance, like fuel contamination. If it's contaminated with water, that would block the feed to the engines. Why? Because when the fuel is contaminated with water, it would be more prone to icing. And if, like the heating system, the oil heating system for the fuel that avoids the fuel from being cooled or from being, from icing, which can lead to a starvation to the engine. Okay, so when you have that type of blockage, that would affect the engine performance definitely. Okay, or icing, it can be icing in the engine itself, or blockage of some type in the engine system. For instance, I'm reminded by an incident that happened with a DC-10 or DC-9. I don't remember exactly where. During takeoff, there was so much ice on the wings, and since the engines themselves are mounted above the wings, so during the takeoff, the ice broke off the wings and went right into the engine. Okay, on both sides, which caused an engine flame out, and you know, which led the pilot to perform an emergency landing. Finally, partial fuel starvation or contamination, which we addressed moments ago. So it can be caused by contamination of the fuel with water, which leads to icing and starvation. It can be a problem with the valve itself that allows the fuel to be ingested by the engine and controlling the flow of that kind of fuel. Or it could be a problem of the engine itself. No, problem with the engine won't have anything to do with the fuel itself. Yeah, mainly fuel starvation. So the fuel is no longer available on board, or like a wrong measurement of the fuel level that led to the fuel being exhausted without the crew being alerted that it wasn't enough for the trip, or contamination, so it was blocked from the fuel gauges. Okay, now, or fuel leak, for example, which also had led to a starvation in in multiple trips. It has been problematic. Now, the engine power output can be expressed as P is equal to eta times mf times q, where the engine power output is given by the combustion efficiency, how much percentage of the fuel is being combusted correctly, that's eta, multiplied by the fuel mass flow, times Q, which is the calorific or, fuel calorific value. Okay? A reduction in any of these variables results in partial power loss. Pilot actions, troubleshooting generally follows fuel selector check, mixture adjustment, carburetor heat or alternate air, and ignition system check. Okay, so troubleshooting involves these different checks. So the fuel selector check, getting the fuel current level, the adjustment for mixture between the fuel and the air, which is usually by the propellers in smaller aircraft, carburetor heat or alternate air in smaller aircraft as well. Okay, there might be, there is an alternative for that also in modern aircraft systems. And ignition system check. Engine overheat. Overheating occurs when thermal energy exceeds cooling capacity. So the thermal energy being generated, it is exceeding the capacity for, to cool that temperature, the cooling capacity. So indicators include high cylinder head temperature or CHT, which would be, the cylinder head in turboprop engine aircraft. Okay, so measuring the CHT would indicate for us whether the engine is operating normally or if there's an overheat and a potential danger for a fire to erupt. High oil temperature, also the temperature of the oil is necessary to be monitored because it provides whether there is lubrication in the system or not. Rising EGT, so if the exhaust gas temperature is rising, it indicates a potential overheat of the entire engine on the inside, and it could be a predecessor or like an action preempting, like preceding a fire within the engine itself. Common causes, lean mixture. Okay, so it would be an imbalance between the oxygen or the air versus fuel, insufficient cooling airflow. So the airflow is insufficient for the cooling. That's why the engine is overheating. And excessive power settings, which means that the RPM or the tachometer is exceedingly high. Okay, the engine is rotating above the average or acceptable value, which should only be done, okay, it should only be running at that level during takeoff and not for a long period of time, by the way. As a side note, let's explain what lean mixture means. So, this indicates the case when you have an excessive amount of air compared to the presence of the fuel within the engine, which is more fuel economic. Okay, so it would give you a better fuel economy. However, it would lead to an excessive heat and temperature within the engine. So, it should be cooled by a richer setting. Rich mixture indicates more presence of fuel in respect or like in comparison with the presence of the air, okay, which contributes to cooling the engine, having a better temperature for the engine, but it has its own drawback that it incurs a higher consumption of the fuel. This is mainly controllable, in the cases of smaller aircraft. That would be more predominant. Engine overboost. Overboost occurs when manifold pressure or turbine speed within the engine exceeds design limits. So the manifold pressure becomes much greater than the maximum allowable pressure within the engine. The consequences would include usually engine damage, okay, caused by a structural stress, then detonation, which is mainly in turboprop designs, which means that the sparking plug would be firing before the cycle of the gas compression, so outside of the correct or appropriate cycle, and eventually it would lead to engine damage because it would be rotating beyond its design limits. Okay, and immediate corrective action is required in order to prevent a complete failure of the engine. To give you an example, the Qantas flight once, which was an Airbus, by the way, 380, something like that, had a stub pipe which was going into the engine, of course, designated for the lubrication. So that stub pipe within the Rolls-Royce engine snapped once because it was a fault in the design. It broke and released all the oil within the engine itself, causing an overheating of the engine and an over speeding, like over boosting, because the combustion was so unbelievable that it made the main rotor disc go beyond, way beyond its design limits, rotating with an unbelievable power and momentum. Okay, and adding to that the overheat, because it heated over to 6,000 degrees, it broke off. Okay, and it was released with an infinite energy going through, puncturing the wings and other areas of the front frame. Okay, nearly brought down the aircraft. So it was due to over speeding. Okay, which led to a structural stress against, the rotor disc itself, which was made, by the way, of one of the most robust materials. I think it was titanium. It broke off and it caused the ripping of the entire engine and punctured through the airframe and the wings. Okay, and led to fire also. So they had to extinguish the fire and roll back the engine before that, of course, to idle before rectifying. Yeah, it was hard to rectify the problem. Actually, the engine was down completely, okay, but it affected even the other controls of the airplane. Why? Because it had punctured against the hydraulics. Abnormal indications, abnormal engine indications may result from real system degradation within the engine, like the rotors, the blades, or sensor or indication errors, such as the thermal sensor. Cross-checking is necessary for that reason between multiple parameters and multiple instruments, and it is essential in order to confirm engine health and to be able to assess the engine failure, to verify whether it's a failure or not. Engine fire, ground and airborne scenarios. Okay, engine fire on the ground. Ground engine fires often occur during engine start, for example, because of a leak or whatever other reason, fuel priming when refueling, okay, maintenance operations and miss approaches in maintenance. Priority actions include, first of all, continue cranking if applicable, fuel shut off, shutting off the fuel very necessary, mixture idle cut off in order to choke the air within the engine so as to put down the fire, and fire extinguisher deployment. This is usually during mid-air as well. Now, I want to talk a little bit about why do we continue cranking the engine although there's a fire within the engine. First, we need to make sure that we've checked two items that we need to cut the power, okay, like shut off the ignition and cut the fuel. This is basically what we would be doing, okay, while cranking the engine. Why is that? So that any fire would be fully consumed and pulled out of the exhaust in order to completely like burn out whatever remaining fuel that is in the engine so that it wouldn't escalate, it wouldn't like increase and be overheating and going into the airframe itself. So you would burn out any remaining fuel while cutting any flow from the mixture, okay, so that no more fuel would be added to the engine. More than that, the igniter would be also shut off so that any amount of fuel or fire, okay, would be burned and thrown out of the exhaust to make sure that the fire has been completely starved and pushed to the outside, okay? This is the trick behind that. And I know it might seem counterintuitive, but it makes so much sense when you understand as to why we go through that very procedure. Engine fire in flight. An in flight engine fire is an immediate emergency. So you need to immediately ask for vectors in order to land the aircraft. Okay? But before, you need to assess where it is happening, what are the systems affected, the controls of the airplane, whether they would stand or not. Okay, many things come into play due, to the emergency and the criticality of the problem. So, rapid escalation. These are the characteristics of a fire on board in mid-flight. Rapid escalation of the fire because too much oxygen is running into the engines. You'd have structural damage risk, okay, due to overheating and deterioration. That would lead to deterioration of the blades on the inside of the engine, potential loss of the aircraft itself, okay? And the fire intensity can be modeled as Q fire, the calorific energy or the thermal capacity of the fire is directly proportional to the mass of the fuel, correct? That is on board. That would be consumed fully if the fire persists, okay? And that's why you would need to cut off the fuel from the engines immediately. Thus, fuel cutoff is the most effective mitigation. Typical memory items is fuel shut off, engine roll back to idle, then shut down, and fire suppression system activation. 4.4 Complete engine failure. Okay, let's start with single engine aircraft. In single engine aircraft, usually turboprop, engine failure results in immediate loss of thrust. So here we start assessing the glide performance which becomes critical. The gliding is when the aircraft is only relying on the aerodynamic flow around the wings without any power of thrust so that it can sustain itself in the air as long as possible while dropping down gradually and predictably through, into the atmosphere, of course, definitely. However, when the aircraft has a large aspect ratio, like long and large wings, it would go further, okay, and perform better after a loss of engine, unlike when you have an aircraft mainly relying on engines for thrust like Hercules, which are not aerodynamic aircraft, so to speak. Okay, so when they lose engines, it would be very hard for them to be kept in the air. L over D max designates the best glide ratio, where L is the loading factor of the aircraft mechanically, and D max is the maximum gliding distance, okay, on the horizontal level. Horizontally, what would be the maximum gliding distance? So the glide distance is given by D equal H, which is the height, altitude above the ground, times L, the loading factor, divided by D max, the maximum horizontal range, okay, gliding range possible, based, if you will, on the position or the angle. So the immediate priorities would be establish the best glide speed so as to give you the highest range possible. Select a landing area, the best landing area that you can afford, whether, of course, preferably on an airport runway or on a plane, and attempt restart of the engines during that time. So as you establish the maximum gliding distance through the most optimal glide speed that would get to, the longer time during flying, you can have enough time that would grant you, enough room for troubleshooting and attempting to restart the engine. In multi-engine aircraft, however, engine failure introduces asymmetric thrust, which means that one side of the aircraft would be pushing stronger than the other side. So you would have a forward traction force or thrust force, which is pushing the aircraft on one side more than the other side, where you have a loss of engine power. The yawing moment, which is due to this asymmetric or asymmetric force, is given by M equal TD, where T is the thrust difference, because you might not necessarily have lost the entire engine on one side, but it might be partially paralyzed, okay, or the thrust might have been partially disrupted. So the thrust difference multiplied by the distance from the center line to the engine, okay, from the center line of the aircraft, not the distance between the two engines, but the distance from the center of the aircraft all the way to the engine, to one of the engines, okay, multiplied again by T, which is the thrust difference between two. That would give you the yawing moment, or the moment of rotation around the center of the aircraft, from, and the radius of that moment of that rotation being established from the rudder all the way to the center line of, which is almost next to the center of gravity. Okay, critical considerations: maintain control above VMC, okay, velocity, the minimum velocity, correct engine identification to identify which engine had gone down or had a loss of thrust or malfunctioning, and feather the failed engine. Okay, feathering the failed engine, so that, and this is what we mean by that. You see, especially in the turboprop system, okay, like the blades of the engine would rotate around their axis, okay, so as to increase the angle of attack with the air or to decrease it. So in order to reduce the drag, you need to feather them, meaning reducing the angle of attack with the air, so as to make these blades almost flat, okay, flat to which, in other words, they would be 90 degrees, almost the blades themselves would be 90 degrees against the air attacking them, okay? So you would remove that angle so as to make the aircraft blades no longer eating up more air, okay, except they are no longer biting the air, but this would induce drag when the engine had failed. This is what feathering means. Another point, by the way, is that VMC is the minimum control speed with one engine not properly running. Okay, so with one engine not or non-operative in multi-engine aircraft, VMC is the minimum velocity for controllability of the aircraft. Engine out identification. Incorrect engine shutdown is catastrophic. Okay, why? Because it may result, and it had resulted at times, in complete power loss. Because now you would have both engines out, and the generator, which is connected to the engine, the turbine, would no longer be working so as to generate enough power to run the entire aircraft, and especially the main instruments. Okay, you would have to deploy the RAT or the ram air turbine in such case. So the standard identification logic would be dead foot equal dead engine. In other words, when your foot on the rudder is no longer being able to yaw the airplane from one direction to another, okay, so that would be the indicator on where the engine is dead as well. Okay, we're gonna extend on that. Also confirm with engine instruments like within the ECAS by monitoring the different indicators of that engine. So the oil pressure, the EGT would be very low, okay, and the N1 and 2 would be rolling back for that defected engine. Also verify before feathering. We need to verify before making the decision to feather the engine. Going back to dead foot equal dead engine premise, okay? So what is that concept? What does it actually mean? You see, let's say you have the left engine out. It doesn't matter how deep or how strong you step on the left rudder in attempt to yaw the aircraft to the right, it would still be pushing to the left against your own force, against your own action of stepping on the rudder. Why? Due to the fact of the asymmetric thrust, where the right engine would keep yawing the aircraft, would keep having the tendency to yaw the aircraft to the left side, okay, leftwise. So even when you step and overstep on the left rudder, you would feel it is very sluggish and it's not actually producing the desired results. This is why you would need to actually trim the rudder, okay, in order to maintain a specific balance, okay, preventing the aircraft from rolling. There was an incident, by the way, that I just remembered where an aircraft had, the crew had misdiagnosed a faulty engine while the engine was running normally, but they had rolled it back all the way to idle. So during landing, they had to, because as you go down, the air becomes more thicker, so the thrust would become stronger on one side against the other, the asymmetric thrust. So the aircraft started rolling on one side due to the engine being rolled back on one side, and also since it was rolled back and the pilot had misdiagnosed that the engine was had failed, so he needed to correct the situation because it was no longer generating thrust. Okay, it was no longer climbing. So this was during the landing. He pushed the second engine all the way to full power, which even made a bad situation worse. Why? Because it had increased dramatically the asymmetric thrust between the right and the left engine, which caused the aircraft to roll to the left with an extreme bank angle, and it plummeted to the ground. Okay, this is how serious it can get. 4.5 Forced landing and precautionary landing logic. Let's start at first with forced landing. A forced landing is unavoidable, meaning that you cannot get out from it, you cannot avoid it due to loss of propulsion. So you no longer have thrust, you no longer have a power, a force that is pulling the aircraft forward in the air, so you would have to perform an emergency landing. The decision logic would be engine failure leads to immediate landing required because you can no longer stay in the air more than a specific limited margin of time. Okay, after that, the aircraft would be, since it is gradually plummeting, in the atmosphere and dropping in altitude, it would eventually hit the ground. So the key priorities would be controlling the aircraft, maintaining a suitable gliding speed. Yeah, it hasn't been mentioned here. Yeah, it's part of the aircraft control. Spotting or finding a landing area, the closest one, that is possible, that is affordable. After communicating with ATC, also trying to guarantee is a survival for the occupant. So trying to perform an emergency landing the safest way possible so as to guarantee the safety and the survival of the occupants, of the passengers. 452 precautionary landing. A precautionary landing is a planned landing with engine power still on, still available. However, the engine itself is no longer reliable, so to speak. You cannot trust it to keep running soundly, okay, to keep performing. Like, you're not sure at what point you might lose the engine or it might fall apart, so to speak. So it is used when engine reliability is uncertain, you have a malfunction in the engine, such as a fluctuation in the RPM, in the tachometer, indicator, and continued flight would increase risk. So you need to land as soon as possible. The decision threshold would be R, continue. So the risk level of continuing would be greater than the risk of landing the aircraft. Decision philosophy, early conservative decisions improve outcomes. So you would need to promptly act and not wait a longer span of time, because something that had started as a small problem would become bigger as time progresses, and it would be harder for you to fix the problem, especially when you are in mid-flight over the ocean. Okay, so it would be better to get back to the airport as long as you are still closer to the runway. Okay, so decision philosophy, early conservative decisions improve outcomes. Most survivable accidents occur when pilots delay landing, okay, after reorganizing engine abnormalities. Now, this last part may seem counterintuitive to what we were saying when it comes to promptly act and try to get down as soon as possible. However, you need to first assess the problem and stabilize the engine, go through your checklist, lest you would be performing a sudden action that is out of place and that would be more dangerous than, staying in the air for a little bit longer itself. Okay, why? Because you need to assess the performance of the engines and to maintain, stabilize their operation while isolating the different faults before you go down to the runway, basically. Finally, engine malfunctions demand rapid prioritization, correct diagnosis, and disciplined execution. Partial failures require careful monitoring, while complete failures demand immediate control and decisive action. Okay, when it comes to complete failures that are less tolerable than a a slight malfunction within the engine itself. Understanding engine behavior, performance limitations, and failure logic is essential to preventing escalation and ensuring survivability of the aircraft, both the aircraft and the passengers, and also, of course, the crew on board. Chapter 5 or Module 5, Fuel System Emergencies. Okay, overview of aircraft fuel systems. So aircraft fuel systems are designed to deliver a continuous flow, uncontaminated, okay? So uncontaminated supply of fuel to the engines, both of the engines in case of multi-engine aircraft, or if four, then it would be the four engines, under all operating conditions, which means hot weather, icing, it doesn't matter. It should guarantee an undisrupted flow of fuel to the engines. Core functions include fuel storage within the tanks, especially in the wings, fuel metering, so the measurement, level measurement of the fuel within both tanks and the middle tank in larger aircraft. Of course, their location would be different in smaller aircraft. Fuel pressurization, so as to avoid having bubbles and gases that would block, okay, due to exceeded pressure, they would block the flow of the fuel from the tank all the way to the engine. Okay, so you would have a gas blockage that would push the fuel away from the engine, leading to basically fuel starvation. And finally, fuel distribution between both engines, for example, like the cross feed valve, which is a valve that you would open up to transfer fuel from left tank to right tank or vice versa in order to maintain the equilibrium, okay, and a symmetric weight on both sides of the aircraft so as to avoid it, avoid a roll motion from one side to another due to a, an imbalanced weight, okay? Any interruption in these functions can result in power loss or engine failure. By the way, I wanted to talk about the fuel metering. So how to detect the presence of fuel or the lack thereof, okay? So you would have a sensor, okay? Usually a floater would be, not a something running on power, okay? Of course. So the floater, when the fuel would get to that floater, it would go up, and within it you would have an internal circuit. So for that circuit, it would, for example, open up. It becomes, from a closed circuit, it becomes an open circuit. This is detected in the electronic board, and it would be like a fuel or a level detection that would light off a value. Okay, so the fuel is at 80%, 90%, etc. This would be read by the computer in this way. Another type of level detection, I'm here gonna refer to a type that is used often in water tanks. You would have two probes, like plus and minus wires, okay? And the water, once it gets to the level of the sensor, it would create a short circuit between the plus and minus, and this would be perceived as a closed circuit that would light up a bulb or a LED, okay? Or something within the circuit that would be detected as the presence of water at that level, okay? It would be indicated in water tanks as a LED firing on, okay? Now, when you have a lowering of the level of water from that sensor, so the sensor, the short circuit would be disconnected, because the water is a good conductor of electricity, by the way. So when it goes down, it would disconnect that short circuit, and the light would go off. The bulb or the LED indicator would go off. Of course, in an aircraft system, it would be more sophisticated. It would be an electronic circuit and a computer software that would analyze the different levels, okay, level sensors, and this is how it would assess whether the oil or the fuel, I'm sorry, had gotten to that level or not. Another types of sensor or a type of sensors would be the one that is based on the capacity measurement, the change of capacity. So you have the formula for capacity would be something like, one moment, yeah, C equal epsilon uh, epsilon D over A, I think, okay? Or A over D. I'm trying to remember. Yeah, A over D. Oh, okay, one moment. Let me erase it and draw it again. Epsilon A over D. A is the area of the armature of the capacitor. D is the distance between the plus and minus armature where you have the magnetic field. Now, what changes is the epsilon, which is the permittivity, okay, the dielectric constant. So, when what used to be air between these two armatures is replaced by the fuel getting in between that these two armatures of the capacitor, this would change the capacity value here in farad, and this would be perceived as the presence of fuel, okay, which would be detected in the board as, okay, you have like the fuel at midsection or at 90% or you are full 100%, okay. This is how they estimate the mass of the fuel, by the way. Fuel starvation versus fuel exhaustion. Okay, let's start with the fuel starvation. Fuel starvation occurs when usable fuel is present but cannot get to the engine. So it is present on board, but it is not being delivered to the engine for one reason or another. For example, due to fuel contamination, due to the pressure, like the presence of air bubbles, okay, like presence of gas within the pipes that are preventing the flow of the fuel, okay, just like the water pump would get stuck turning without pumping the water. Why? Because it is filled with the air that is blocking the water flow, that is pushing against the water flow. So here you have the same concept. Or the fuel waxing, meaning that due to icing conditions the fuel had waxed and having been contaminated with water, so it is no longer being or flowing freely within the pipes, and it has been blocked from reaching to the engines, okay. Or blocked fuel lines or filters due to the presence of other types of contaminants or objects that have been forgotten within the fuel tanks, okay. Air ingress into the fuel system, which what we've mentioned moments ago, that would block the flow of the fluid. Fuel flow rate can be expressed as the following: the mass of fuel, or the flow rate, yeah, that would be fuel mass flow rate, is given by rho AV, which is also called volumetric flow, by the way. Rho, which is the fuel density, okay, multiplied by A, or the cross-sectional area of the pipe, times V, which is the velocity of the fuel. Okay, so here A times V is actually the volumetric flow, which is the cross-sectional area of the pipe multiplied by the velocity of the fuel flowing within the pipe. You multiply that, since it is the volumetric flow. When you multiply it by rho, which is the density in kilograms per meter cubed, you would get the mass flow rate, the fuel mass flow rate. Fuel exhaustion, which means, in other words, when the fuel is no longer available on board. Okay, the fuel exhaustion occurs when all usable fuel has been consumed. So you're out, okay? Your tank had become empty, in other words. This can be due to fuel leak, to other reasons. We're gonna see that. Okay, so in other words, the mass of the remaining fuel is equal to 0. You're empty. You're flying on empty tanks. The contributing factors would be, and it had already happened in the past, by the way, inaccurate fuel planning, okay, unexpected headwinds. So the headwinds would cause, an excessive burning of the fuel, so as to counter the force that is pushing against you, okay. So due to that factor, you would burn over the budgeted fuel for the flight, and suddenly, due to that factor not being counted in or accounted for, you would find yourself running on empty, okay. And fuel leaks, okay, fuel leaks, so you would have a puncture in the fuel tank, for example. Now, When we talk about the inaccurate fuel planning, this also can be a miscalculation of the fuel, and it happened before. They converted between, or they misused, they kind of confused between the metric measurements and the imperial, and they ended up on empty tanks in mid-flight. Okay, the pilots, the ones that miscalculated were the maintenance engineers on the ground. This happened in the Gimli glider event, where actually the pilot did a great job and he kind of slipped the aircraft sideways and landed on a runway that was used at the moment as it was an abandoned runway that was being used as a race arena. Okay, so unlike starvation, fuel exhaustion is irreversible in flight. Like, you cannot get out from it because you no longer have anything. You're running on empty tanks. Operational differences. So starvation may be recoverable. However, exhaustion results in total power loss, total engine rollback. Correct diagnosis is critical for appropriate action. So it is very important to be able to assess what is exactly happening, whether you have enough fuel and the engines are being starved due to contamination, or whether you no longer have fuel at all. This is where cross-checking the instruments come in handy. And of course, like, you need to assess what's happening and the behavior of the aircraft after using the cross feed. Okay, multiple elements need to come into place in order for you to be able to analyze what's exactly happening and which scenario, whether it is starvation, partial starvation, or a full empty tank. Okay, or an empty tank. Fuel contamination and icing. Okay, let's talk about fuel contamination. So fuel contamination includes water, dirt or debris being within or spotted within the fuel, and microbial or bacterial growth. Now, for water, water contamination disrupts combustion, which can lead to engine flame out, by the way, by blocking the fuel flow. And also another thing or phenomena that can happen is icing. Okay, so why? Because since it is contaminated with water, the water, with ice, with the freeze under low temperature conditions, that would also block the fuel from going through because it has been mixed with water. Although they cannot mix, but you get the point, because the water itself would be frozen within the fuel. Now, contaminant concentration can be expressed as C is equal to mass of contaminants divided by the overall mass of fuel. So that would give you 10%, 20%, etc. How much mass of water exists within the fuel, for example, divided by the overall mass of the fuel. Even small values of C can cause significant damage or operational issues. Not damage, so to speak, but operational malfunctioning. Even at times they can cause damages such as detonation within a turboprop engine, by the way. Now, speaking of detonation, let us review how does a turboprop engine work. Okay, what are the 4 strokes of the cycle of a turbo engine, whether within an aircraft, okay, a turboprop aircraft, or an ordinary car. Now, we start with the intake phase. This is the first stroke. So the intake is the phase in which you have the air-fuel mixture being sucked into the cylinder of the engine, which would drive the piston along with the connecting rod here downward. This connecting rod, which is also connected to the crankshaft, it would rotate the crankshaft. This would be the first stage. And by the way, during that stage, the exhaust valve would be closed. Now, once the crankshaft turns, it would go all the way and compress. Okay, so this motion would, in reverse, come back and compress the mixture of air and fuel. And during that stage, both valves would be closed, both the intake and the exhaust. This would guarantee a high compression rate of the fuel-air mixture, reducing its temperature almost to minus 40 degrees Celsius, by the way. This would be, again, the compression stage. So, intake, compression so far. The third stage is the stage in which the sparking plugs, while both valves are closed, would fire up, causing an immense explosion within the cylinder that would lead to a rapid expansion of the hot air fuel mixture, which would drive the piston rapidly downwards while moving the connecting rod and the cranking shaft all the way, around its axis. And the last stage would be during that motion, as this piston moves along the connecting rod, the exhaust valve would open up so as to release, once the piston starts going up back again, the exhaust would release all the gases that are full of carbon monoxide, and then the cycle would restart again. Going back to the event of detonation. Detonation happens when you have a mixture of water with the fuel, which would give more oxygen to the mixture, allowing it to explode before the combustion stage, which is the power stage here. Okay, so before the combustion strike or phase, the mixture of air, fuel, and water would cause a misfiring, okay, within the cylinder, which would go against the cycle's motion, like against the motion of the connecting rod. So let's say the connecting rod is still in the compression stage. Before it goes all the way and stops, the explosion would push right against this connecting rod and, against the piston. So it would be going adversely against the motion of the piston and the connecting rod, damaging both of them due to that adverse action, because it is out of alignment and out of its own correct timing. Fuel icing. Fuel icing occurs when water suspended in fuel freezes at low temperatures, which what we mentioned before about fuel waxing. Fuel temperature is related to ambient conditions. Okay, so temperature of the fuel is around temperature of OAT, okay, operational ambient temperature, minus delta T, which is the temperature differential. Okay, where delta T represents cooling due to altitude and airflow. So it is the difference in temperature due to cooling that is caused by higher altitudes. Ice crystals can block filters, restrict or hamper the fuel flow within pipes, so blocking filters, restricting fuel flow, and cause the fluctuation of power. So you would start noticing a fluctuation of the RPM or the EPR or engine power due to a disrupted, discontinuous fuel flow within the engine. Preventive measures include fuel heaters through the oil. The engine oil would go through pipes that would heat the fuel in order to avoid the waxing, and anti-icing additives within the fuel itself. Fuel pump failures. First, let's start with the types of fuel pumps. You have two main types. The first one is an engine-driven pump, which is a pump driven by the engine itself. As it rotates, it is pumping also the fuel. Second, electric auxiliary pumps, which are standalone pumps that run by the same power that is being generated or provided by the engine itself, mainly. Okay, engine-driven pump failure. So, failure of the engine-driven pump reduces system pressure, correct? So, the power of or the pressure of the fuel would be less than the required pressure, leading to fuel starvation of the engine. Symptoms include fuel pressure drop, a drop in the pressure of the fuel, engine roughness, so the engine is no longer running on enough fuel mixture with the air, so it is highly running on a much higher percentage of air and a lack of fuel, which would lead to engine roughness and an overheating, by the way. Okay, this is why the engine becomes rough due to a rise of the temperature within the engine, which is due to the fact that most of what's being combusted is the air more than the fuel itself. And partial power loss, so you would see the power would no longer be like at times you would have a disconnection of the power in the entire cabin, okay, except in um, for the cockpit. So that would be one of the consequences of the pump malfunctioning. Okay, so a partial drop in power because it needs to be driven by the engine itself. Auxiliary pump activation is typically required in such case. Electric pump failure. Electric pump failure may affect the following performances. Engine starting. Why? Because it is being starved by the feed of the fuel that is no longer enough and reliable. Take off, because you would require a much higher power in order to take off, because you would need full power at some stage, at some point, in order to lift off the airplane from the ground, from the runway, and also high altitude operations. Now, redundancy improves the reliability. The reliability of the system is given by 1, which is 100%, minus the sum of the probabilities of all the systems, okay, being taken down one after the other. So 1 minus reliability probability is actually saying the opposite, okay? So the sum of probabilities of systems, multiple redundant aspects of the pumping system being defected, that sum, when it becomes so high, it gets close to 1, so it renders the system no reliable at all, with reliability 0%. Okay, but when there are no defects in the redundant systems, the reliability would be 100%, which is 1 in terms of probability. This is how you can read the measurements, okay, the numbers. Fuel imbalance and cross-feed errors. Fuel imbalance is when you have the amount of fuel on one tank is higher than that on the other tank, especially when we're talking about the fuel tanks being within the wings and the cross or the midsection of the aircraft, usually larger aircraft. So in such case, you would have one side of the aircraft, let's say the right side, heavier than the left side. So the aircraft would start getting the tendency to roll in one direction, sideways, opposite to the other, due to the asymmetric weight on the right wing. Okay, it would start pulling or rolling the wing down. So basically, this fuel imbalance would harden the controls and would make it a little bit harder to balance or level off the airplane in some instances. And it happened before. Now, how does it happen, or what is it defined in mathematical terms? That would be the fuel imbalance rate, or delta M, is the difference of the mass of fuel between the left wing or the left tank and the right tank. So in other words, delta M is equal to mass of the left wing fuel minus mass of the right wing fuel. Effects include lateral trim requirements in order to, again, in order to reduce the pressure required by the pilots on the controls in order to stabilize the aircraft and keep it level, removing any roll, any bank within the aircraft, bank angle to one of the sides, the left or the right. Second, increase the drag, okay? And third, structural stress. So the drag would be increasing, okay, on one side of the aircraft, and one engine basically would be running more than the other in times, okay? But here we're not talking about the engines themselves, but rather one side being heavier than the other, that would increase drag because of the adjustments uh, done to the controls in order to remove the yawing or the rolling effect of the aircraft from one side to the other. So as you adjust the control in order to counter the imbalance that is pulling the aircraft on one side more than on the other, triggering the rolling motion. Okay, so as you adjust that, the aircraft would be incurring more drags due to that, to these alterations of the controls. Finally, structural stress, because the aircraft is going against the airflow in order to correct that rolling behavior, that would increase the stress against these controls. Real world accident examples. So, fuel mismanagement accidents. Common accident patterns include failure to switch tanks from left to right or to cross feed, misinterpretation of fuel gauges. So, they would have read that the fuel is full. Meanwhile, there was something problematic with the reading. Okay. Cross feed misconfiguration. So, they cross fed, and it happened before. They cross fed the left tank to the right tank or vice versa, I believe. But one of the tanks was leaking fuel and they forgot to like reverse this operation in order to keep the remaining fuel, and they ran out of fuel very quickly. Okay? Very big mistake. Accident probability increases with operational complexity. So the probability of accident is directly proportional to the number of configuration glitches or configuration changes that are erroneous, that are misconfigurations, in fact. Finally, fuel system emergencies often develop slowly and provide early warning signs. Understanding fuel flow, system logic, and common error patterns enables pilots to diagnose issues early and take corrective action before power loss occurs. And so, proper fuel management remains one of the most effective tools in aviation safety. So, proper fuel management is one of the most important things to be taken into consideration for effective and safe flight. Module 6 or Chapter 6, Electrical System Failures. Overview of aircraft electrical systems at first. So, the electrical systems at first provide power for engine starting or power on, ignition and fuel control, fuel pumps, etc., and fuel measurements, all of these things, flight instruments and avionics, navigation systems as well, lighting and environmental systems such as the air conditioner, the gasper, the lighting within the cabin. Electrical power now is typically supplied by alternators or generators. Okay, so alternators are basically AC power. Okay, like they provide AC, alternative current. Generators are mainly DC, but they are both powered by the engines. Okay, it can be the engine itself running and generating power. All right. Um, yeah, basically it is from the engine itself. Generators, we're talking about the DC power that is fed by the engine also. Okay, it's fed, but it is generating a DC direct current power, not alternating current. Batteries as well for emergency, for to be running in case of an engine failure. Yeah, as a backup. Loss of electrical power degrades situational awareness. Okay, so because the indicators and different instruments won't be able to be, displayed any longer within the cockpit. So, like the ECAM and the ECAS will turn off in case of a power loss. So, this may affect engine operation in some aircraft. Alternator and generator failures. In normal operation, the alternator or generator supplies electrical power and maintains battery charge. which is very important because batteries are the last backup, along with the RAT or ram air turbine in case of an engine failure in mid-flight that would be deployed in order to generate enough power so that it can run, the most crucial situational awareness instruments such as the attitude indicator, the altimeter, the VSI, airspeed indicator, etc. Okay, the power of the engine is given by P equal V times I, which is V is the system voltage and I is the generated current. Failure indications. Alternator or generator failure is indicated by low voltage or low amperage indications. So you would have a low power in, as a bigger picture. Battery discharge annunciation. So the batteries would start to drain out, which means that they are no longer charging due to the loss of an input current to them. So the main power source that had been charging the batteries is out, and this would be due to an engine malfunction because the engines are mainly the ones that provide this power. Master caution alert, okay, that would indicate a power loss, an electrical loss due to whatever reason. Failure results in a shift to battery only power. So the power available would only be the battery or the remaining power within the batteries themselves. Common causes would be drive belt failure, okay, which is the transmission that relays the power, like the mechanical power, to the dynamos, which produces the electrical power, okay, in small aircrafts, or like a problem within the turbine of the engine. Voltage regulator malfunction, so the one that the part that is regulating the voltage so as to avoid having an over voltage or an under voltage would be malfunctioning, and overload or short circuit. So short circuit would pop out at times within the cabin. It would pop out the circuit breaker. It can be due to a fire, by the way, or an overload, which means that the consumed power, the power that is being consumed, is much higher than the one being generated by the generators. Okay, so that would lead to a power failure. Battery only operations, battery capacity and endurance. Let's talk about that. So the battery endurance is finite and depends on the load being on the batteries themselves. So the battery endurance in hours is given by the battery capacity in ampere hours divided by the load, which is the current. Okay, so high electricity loads would drain the batteries much faster than during a lower consumption operation. So high electrical loads drastically reduce the endurance, and they would drain the batteries in a very shorter amount of time. All right, now to give you an insight on how to evaluate the endurance of the batteries, I'm going to borrow an example which is taken from the solar energy application, which means that when you have installed a solar system with multiple panels with different batteries and the UPS controller, which is commonly called, by the way, the inverter for common people that are not specialized, but it's not called inverter. The inverter is the last stage. So it is the UPS controller. So when you have that system at home, in order to reduce the electrical bill, this is how we evaluate. And of course, the same method applies here in this context of aircraft. This is how we evaluate the endurance of the batteries for the solar energy system, which can be also applied in aviation. Let's say you have different batteries, like as many as 4 batteries, okay? So you have 4 batteries, each one with the capacity of 200 ampere hours. Okay, that would be the capacity. The 4 batteries are 48 volts each, let's say. Also for residential, they are usually 12 volts. No, not always. Okay, they are usually 48 volts. Now, okay, more than that. So each battery, each of these 4 has a DOD or depth of discharge of, let's say, 90%. They are lithium batteries, battery types. Okay, so what does the depth of discharge mean? It means that once that the batteries get to 10%, okay, they can no longer go below 10% or they would be damaged. So the UPS controller would disconnect the batteries once they get to 10% remaining capacity after the entire discharge cycle. That would be the cycle, okay? More than that, you have the maximum capacity, okay, or the effectiveness of charging would be for lithium, I think around 95%, meaning that you cannot charge them all the way to 100%. It cannot work, okay? They charge at a maximum of 95%, okay? So, and within your house, you have a load of, let's say, 10 amperes, okay? You have a load of 10 amperes at 230 volts, okay? So how to evaluate the endurance for these batteries? So you have the following, okay? At first, 4 batteries multiplied by, okay, so this is, by the way, the power, remaining power, divided by consumed power, okay? Let me clean up a little bit. So endurance is given by remaining power divided by consumed power in respect of time. So that be the available power or remaining power is 4 batteries multiplied by 200 ampere hours multiplied by 95% capacity that you can get them to be charged, which is so 0.95 times or multiplied by the depth of discharge, so they can give you only 90%. The remaining 10% you cannot touch, so it would be times 0.9 divided by the loading. Okay, oh, by the way, since we are evaluating the power, so you need to multiply 200 ampere hour by also 48 volt. Okay, so these are batteries of 48 volts each because the power is equal to VI, correct? Voltage times the current. So you divide that by the loading. So you are loading on the system 10 amperes, okay, at 230 volts, okay? So let us evaluate, okay, one moment, and we will give you the answer on how long they would last. Okay, so that would be 48 multiplied by 4 batteries multiplied by 200 ampere hours multiplied by 0.95, the maximum loading, times depth of discharge, which is 0.9, divided by 2300, the power consumption, which gives us 14.27 maximum hours, okay? 14.27 hours. Exactly. Operational priorities. During battery-only operation, non-essential loads must be shed. They are usually automatically disconnected by the autopilot. Okay? So what remains is navigation and communication equipment in order to communicate the emergency with the ATC, the air traffic controller on the ground, which are the main priority in such emergency case. Flight should be terminated as soon as practical so as to avoid complete loss of instruments and complete loss of controllability of the aircraft. Load management directly affects survival of critical systems. Causes of electrical fires. Electrical fires may result from short circuits, overheating wiring, so that usually is due to the fact that the loading on the current or like the loading on the wires is way more than what the wires expect to handle. So you would have more loading due to whatever reason. Okay, so let's say a wire can handle about 10 amperes and it has a load of over 20 amperes. So this would overheat the wires, causing it can even lead to an incendiary phenomena, incendiary event, or a fire. Also, insulation breakdown, which means that there's an electrical surge between plus and minus wires. Okay, there would be an electric spark between the two wires that are oppositely charged, okay, or that have different poles. This spark can create a fire as well. Heat generation in electrical components is given by Q, which is the heat energy, is given by I squared times R times T, which is the time, okay? Resistance, so mainly the power multiplied by time. The power is Ri squared also, or VI, because V is equal to Ri, so it would be Ri squared multiplied by the time. It would give you the heat energy being generated. Immediate actions. Electrical smoke or fire requires immediate prompt action. First, power reduction or shutdown when you have a suspected engine or a suspected like a section of the aircraft that can be, it's not necessary, or it's something, a wire that's feeding the power to a secondary equipment that you can actually abandon, so to speak. So you need to shed that power and to cut or break the circuit, okay, activate the circuit breaker in order to cut the power to that section. Electrical isolation, so isolate the problem electrically so as to not have an escalation or an increase of the dangerous situation. And smoke evacuation, so pushing away the smoke that has been generated due to that event, okay? Now, fire growth rate is directly proportional to electrical current flow within, okay, within the wires. Another point that I need to focus upon here to bring more attention to, which is the fire growth rate, okay? Why is it directly proportional to the electrical current flow? You see, the current is like the flow of water. It needs to go unconstricted through the wire. When you have a constriction, okay, what happens is that the excessive energy that, or the excessive flow that has failed to go through the wires, it needs to be converted somehow to heat, okay? Why? Because it needs to escape. It's like having a highway where only 3 cars can pass through the lanes at the same time, but you have around 10 cars, okay, that need to pass at the same line, okay, but you don't have actually 10 lanes. So what happens in such case that the cars would need to wait. In electricity, there's no waiting. The power needs to dissipate one way or another, usually as an energetic, or like in heat form, okay, in heat energy form. So the current would go and would overheat the wires, being converted to heat, to high temperature. This is what would cause incendiary phenomena. Now, as the current becomes much larger than what the wires would take, it would be more would be converted to heat energy that would increase the temperature of the wires, and even, causing, for example, the isolation being broken or snapping, and leading to a potential fire that would start gradually with the smoke. That smoke can develop into a fire due to the overheating phenomenon. Electrical buses. Electrical buses distribute power to system groups. Typical buses include the main bus, the main power bus, which is the main distribution array of lines coming from the main power feed of the engine. Then you have the essential bus that feed the main instruments on the aircraft, and the avionics bus, okay, the navigation and other things, okay, but they are grouped based on priorities and grouped in a way so as to isolate different systems from each other and while providing some kind of redundancy in the power feed. Bus failure effects. Bus failure results in loss of all the connected systems underneath it. So when the power of the bus is equal to zero, everything that's connected to that bus would fail electrically, would be shut down, despite the availability of the power elsewhere, which means on other buses connected to other alternative systems. Load shedding strategy. Load shedding reduces the total current draw or consumption, so to speak. So the total current is equal to the sum of different currents coming for or being consumed or drawn from different loads within the aircraft. Reducing I total increases battery endurance, as we mentioned before. Okay, this has been proven by the formula. So automatic load shedding is needed, and it may occur in advanced aircrafts due to a specific malfunction or when you have the aircraft running only on batteries. So only the most crucial instruments would still be running on battery while shedding other types of instruments. So while manual shedding is required in simpler systems, you are required to perform manual shedding, manual braking, or outage, so to speak, if I can use the term, of different instruments and turning them off by disconnecting them from the battery draw, from the power bus, using the circuit breakers so as to only sustain the most crucial instruments that are vital to continue the flight and to have some controllability. Actually, not controllability, but rather situational awareness over what's happening and where are you in the flight when it comes in terms of position or heading and attitude, altitude, VSI, and airspeed. Glass cockpit revisionary modes. Okay, let's talk about glass cockpit dependence. Glass cockpits rely heavily on electrical power for the PFD or primary flight display, which is a monitor, a system like a screen with a computer behind it, MFD or multifunction displays, and with them the integrated warning systems, because warnings come through these displays, these computerized integrated displays that would visualize different outputs coming from multiple instruments at the same time. So you would have the attitude indicator along with the airspeed to the left, the altimeter, which is the altitude indicator, to the right with the VSI also. Also, you would have the different warning systems, such as when you are about to enter a stall, you would get a dashed line, red line, okay, coming from below all the way to the airspeed cursor. That would be like a preemptive warning that you're about to enter into a stall, which is very important. And different types of alarms, such as, or indications, notifications, such as when you are entering, when the aircraft is entering in retard mode, which is right before the touchdown. This is the flare mode of the aircraft, where the nose would be automatically pulled upwards. This is in the Boeing. I don't know if the system is there still, like the way it used to be, automatic. Okay, so the nose would be up, and the engines would be pulled back, would be rolled back to idle. This is right before the touchdown on the runway. So that mode would be indicated, it would be notified on the screen by the word retard, which means that the aircraft is in retard mode right before touchdown. It's about to touch on the runway. 662 revisionary logic. Revisionary modes allow limited display capabilities after failures. Okay, so when you have a failure, you need a limited display capability that is minimum so as to be able to troubleshoot. Typical strategies include PFD or primary flight display slash multi-function display consolidation. Okay, so you need them to be aggregating everything that you need to know, all the notifications and alerts. Backup battery activation, so the backup battery should go on at that moment. It should be activated, and the systems would be running on battery mode, and independent standby instruments, which are also other analog instruments that are needed as backup in case the power goes down. Okay, like a standby attitude indicator, for example. Display availability can be expressed as A, which is the display availability, the availability being A, is equal to T powered, okay, the time that the instruments can be powered divided by the time required, okay, to be, for the power to be consistent in order to make a safe landing, for instance. 63, pilot responsibilities. Pilots must recognize display failures quickly so as to identify the type of fault. For example, when you have an engine flame out, you would run off the power really soon. Select correct revisionary modes, meaning know which displays are the most crucial so as to keep them running, and what other systems need to be shed out from the electrical bus, and transition to standby instruments if required as a backup. Finally, electrical system failures degrade aircraft capability progressively rather than instantly, okay? Because it is about a gradual discharge of the remaining power in the batteries. Early recognition, disciplined load management, managing the loads in terms of knowing which loads to shed out from the power bus, and correct use of revisionary systems are critical to maintaining control and situational awareness. Okay, so you need to know how to use revisionary systems, which is critical in order to maintain the controllability of the aircraft and situational awareness, as we mentioned before. In modern aircraft, understanding electrical architecture is as important as understanding aerodynamics during emergencies. Chapter or Module 7, Flight Instrument Failures. Let's start with the flight instruments overview at first. So the flight instruments provide essential information regarding the following: aircraft attitude via the attitude indicator, which is the bankroll, like how much of an angle the aircraft is banked to the right or to the left, or whether it's leveled and horizontal, like flying without any rolling movement. The airspeed, which is measuring basically the speed of the aircraft within the air, okay? But practically, it is measuring the speed of the air going through the pitot tube. Altitude, which is the altitude in reference of the ground altitude, okay, the runway. And it is based on the measurement in reference of the differential of pressure, because as we climb, the pressure goes down, okay, it decreases the atmospheric pressure, that is. Vertical speed, or VSI, which is the rate of ascent or descent, and this is the rate of change of the pressure, the atmospheric pressure. So it is the speed of change of the atmospheric pressure, not the difference itself, but the rate of change, the speed of change between one atmospheric pressure value and the other as the aircraft ascends or descends. Most traditional instruments rely on either the pitot-static system, as we mentioned, and the gyroscopic principle. So you'd have a directional gyro, like a gyro rotating at a high speed that would maintain the heading, okay? And of course, it needs to be readjusted and updated, synchronized, in other words, with the main magnetic compass. Okay, also the gyros are used for the attitude indicator because they would remain stably rotating in the horizontal direction, no matter where or how the aircraft is moving to the right or to the left. Failure to these systems can lead to misleading indications rather than complete loss, increasing the risk for accidents. Pitot-static system failures. Let's start with pitot-static fundamentals. So this system measures airspeed, altitude, and vertical speed using pressure differences between the static pressure of the air that is locked within okay, that has been captured when the aircraft was still on the ground on the runway, which would be designated as level 0 or altitude 0, and the external pressure of the atmosphere at current altitudes. So at these altitudes, this is how the system would measure the altitude based on the differential between the external pressure and this pitot-static pressure. Okay, so that would cause the diaphragm, which is like the magazine where you have the trapped air on the inside, it would dilate as the differential or the difference between external pressure and internal pressure increases. So this static pressure, which was collected, which is for the air collected on the ground, is larger than the external pressure as the altitude increases, which would make this diaphragm dilate. And as it dilates, it would rotate the needle, indicating the current altitude. Now, for the VSI, it's a little bit similar. However, the VSI, for the VSI, the diaphragm would retain its own shape, its original shape and form and volume. But what happens is, as the aircraft climbs or descends, this differential of pressure would make, during climb, this diaphragm dilate, okay, like a stretch, or compress during descent. But then after compression, so as the pressure keeps changing, it would keep compressing. But once the aircraft levels off on a specific altitude, it would retain, this diaphragm would retain its original shape and its original volume. This is how it measures the vertical speed. As for the ASI or airspeed indicator, it works by measuring the velocity of the ram air which is entering through the pitot tube, okay? And this is called dynamic pressure. It would be measured in comparison with the static pressure of the diaphragm, also locking static air on the inside, okay? The static air on the inside. So this differential of pressure would indicate the current velocity, or like the true airspeed. Not the true airspeed, there would always be some error difference. Now, for the formula of the dynamic pressure is given by Q equal 1/2 rho V square, where V is the velocity or the current airspeed, Q is the dynamic pressure, and rho is the air density. Okay, from that, you can get the current velocity or airspeed. Now, to give you how to get the current value of the airspeed, so you have here Q is the dynamic pressure. Okay, so 2Q would be equal to rho V square. So V is equal to the square root of 2Q divided by rho. This is how you measure the current airspeed value. Okay, now, by the way, another thing to be noted here is that we have two heaters in the pitot-static tube so as to guarantee that it won't be blocked due to icing, which is very important because icing conditions can contribute a lot in bringing or causing failure, instrument failure, especially whether in the pitot-static tube. It can cause failure of the engine flame out, or excessive drag on the wings. So it's very important to have heaters and different mechanisms in order to de-ice the entire aircraft. Common pitot-static failures are blocked pitot tube or blockage of the static port, where you would have the measurement difference between the current external pressure, ambient pressure, and the static pressure, and leaks in pressure lines. So the pressure lines that feed into different instruments, if you would have leaks, then this would cause erroneous measurements. Each failure produces distinct instrument behavior. To give you an example, in one of the air crash incidents, an aircraft had its own left pitot tube partially blocked by an insect that had created its own web on the inside of the pitot tube inlet. This manifested during takeoff as a lower airspeed than normal. Why? Because at lower altitudes, especially at ground level, the air density would be much larger, so the airflow would be constricted within the pitot tube, which depends on the speed of this airflow in order to measure the airspeed. So this manifested as a lower airspeed than normal, but once the aircraft became airborne and as it started increasing altitude, in altitude, okay, since the density drops with altitude, the airflow became more fluid. It started flowing not only more smoothly, but even more rapidly, which is, it started being detected by the aircraft computer systems as being an overspeed. Actually, what was weird about it is that as an overspeed indication or alarm started going off within the cockpit, at the same time, moments after, the stall warning came off. Okay, tactily, which means that as a motor sensor, the stick shaker started acting up as a warning for stall. Why? Because the sensor of stall, so in other words, the aircraft was actually going much slower than it was indicated on the indicator on the screen. This is due to the fact that the airspeed was increasing, okay? Meanwhile, the stall warning, the stall sensor, which is a completely different system, had detected that the angle of attack of the air was going upward. It's like an updraft. It was no longer, showing that the air was flowing normally around the wings. In other words, the wings were no longer generating lift. This is why, it caused a major accident on that event. Also, despite the fact that what I'm about to say is, is not related directly to the pitot-static system, has nothing to do with it in a direct manner, but since we brought up the icing conditions, so when we talk about icing, also the icing has major consequences on the engines. So when you have icing conditions, this would block, the ice crystals would block the engine inlets that feed oxygen or air to the engine in order to provide a mixture with fuel so that the engines would run smoothly instead of flaming out. So when you have an accumulation of ice and it's not dealt with through the engine de-icing system, which would overheat these areas of inlets so as to melt the ice and prevent any blockage, this can lead to engine flame out. In other words, you might have problems with the de-icing system within the engines, like the engine heater. Blocked pitot versus blocked static port. Blocked pitot tube, when the pitot tube is blocked but the drain hole remains open, which is by the way necessary for the measurement of the VSI, since the pressure would be draining slowly out of that hole, and this would guarantee that once the aircraft had stopped climbing or descending, which means had stopped changing from positive rate of climb to negative rate of descent, and the differential of pressure has settled, it's no longer like changing, so the needle would settle at zero, designating or like indicating that the aircraft had leveled off. It's no longer climbing nor descending. In other words, there's no longer any differential of pressure going on. The pressure had stabilized. This is the main purpose behind the draining hole that would open up during climb and or after climb and descent. Okay, so now during and after, if the pitot tube is blocked but the draining hole remains open, the dynamic pressure reduces to zero, which is the ram air drag, the ram air pressure. Okay, so since no air is moving into the pitot tube, the airspeed indication would become zero, as if the aircraft is on the ground, it's not moving. So when both pitot and drain are blocked, however, the airspeed would have, the same behavior of the altimeter. It would start dilating just like the altimeter does, so as to show the differential between its locked static pressure and the external pressure. Okay, so the needle would start turning just like the altimeter measures the altitude. Now, the indicated airspeed is directly proportional to the pressure of the pitot static tube of the pitot ram air minus the pressure of the static air that is trapped. Okay, resulting behavior. So IAS increases during climb and indicated airspeed decreases during descent. To make something clearer, by the way, and this is what explains that the IAS or indicated airspeed would increase during the climb and decrease during descent when the pitot tube is blocked. You see, when the front of the pitot tube, which is the inlet, is blocked somehow, this would cause an increase of the differential of pressure between internal pressure, static pressure, and external pressure during climb, and decrease or compression of the diaphragm during descent. So the difference between external air pressure and that of the internal one would start decreasing this gap, so compressing the diaphragm and turning the airspeed upward. Okay, so this is how actually it changes based on the airspeed. Blocked static port. With a blocked static port, you would get static pressure, which would be trapped, and hence altimeter and VSI would freeze, the vertical speed indicator. Why? Because airspeed error occurs due to the fact that the indicated airspeed error is given by the square root of the difference between the pitot pressure and the static trapped air pressure. Okay, so square root of pitot pressure minus static pressure. The effects would be manifested as overread in climb, so overreading in climb and underreading in descent. A differential of the values between the real value and the indicated value, both during climb and descent. To give you more insight, so this is the static port over here. What will happen is that due to a partial blockage or even at times full blockage of the static port, what you would get is a lesser degree of freedom for the breathing, for like the static port to breathe. So during a climb, there would be an overreading of the differential of pressure. Okay, so it would be overreaching above the actual real value for the altitude and underreading in descent. So during descent, this compression that should be taking much faster, it would be slower. Okay, so the designated or indicated altitude would be larger than the current altitude. Okay, and also the VSI itself would be affected. Unreliable airspeed scenarios. Okay, what are the different causes? Unreliable airspeed indications may result from pitot icing, so icing conditions, multiple sensor failures when it comes to the instruments, the gyros, okay, or multiple sensors at the same time would fail, and data disagreement in glass cockpits. So since you have two pitot tubes, one would be indicating one value and the other would be indicating another value completely different, with a larger margin or gap of difference between both indicators, between both instruments. Recognition. Symptoms would include airspeed disagreement warnings. Okay, so you would have two values for the airspeeds coming from both pitot tubes, but they are disagreeing. They are not the same. Second, impossible airspeed values, which don't even make any sense. So during flight, you would get an airspeed value close to zero. Okay, or overspeed indication while you have like a stall warning. So it is the same thing, okay, which already happened and we've mentioned an example before. Or mismatch with pitch and power. So you would have a positive pitch, a higher power, okay, high power, and you would even hear the engine screaming. Meanwhile, the altimeter is not changing values. It doesn't make any sense because you have so much power of thrust and the attitude indicator would be giving you a positive attitude, okay? Not a positive climb, a positive attitude with a slighter angle of attack, not too much pitched up. Meanwhile, even with the engines running, the indication for the altitude, for the altimeter does not make any sense. And seems as if the aircraft is not climbing at all. Meanwhile, and also you might overcheck it, like check it at the same time with the VSI. These values won't make any sense together. Pitch and power technique. In unreliable airspeed scenarios where the indicated airspeed is conflicting or is not accurate, pitch and power provide reliable performance references. You see, because lift equation is given by L equal 1/2 rho V square, and this first part, by the way, is actually the dynamic pressure, multiplied by S, which is the wing area, times CL. By the way, CL, which is the lift coefficient, is actually a function or like a parameter that is sensitive or is dependent to what is called the aspect ratio. Okay, so it's kind of depending on aspect ratio. What is the aspect ratio, by the way? Aspect ratio is equal to B, which is the wingspan divided by W, or the average wing width. So B actually is the distance between the two wing tips within an aircraft. So you would have this distance from here to here between both tips. That is actually B. And W is the average wing width, average width of the wing. So B over W, that would be the aspect ratio, which is an important factor that affects the CL value, or the lift coefficient. Maintaining known pitch and power settings ensures safe flight until valid airspeed has been restored, whether within the instruments or in the indication, okay, based on where the fault had occurred, usually in the instrument itself. Gyroscopic instrument failures. Let's talk about gyroscopic principles. So these instruments that are gyroscopic instruments rely based on the movement of the gyro, which would be a rotating disc, whether horizontally in the horizontal plane for the attitude indicator, or in the vertical plane for the heading indicator, which is called a directional gyro. That would be, by the way, also synchronized at the same time from the compass heading based on the magnetic north. So these instruments rely on two main factors: the rigidity in space. In other words, they should not be budging sideways or rotating outside of the plane designated for them. So for the gyro rotating vertically, it should stay rigidly fixed on that vertical plane without moving sideways. And precession. Precession means that as it rotates for some instruments, okay, this is used for some instruments as an advantage, okay, to indicate, like, for example, the turn indicator. So the precession is the force that is created due to the rotated motion sideways perpendicularly to the plane of rotation. So, and I will represent it in a moment. Angular momentum for the rotation is given by H is equal to IW, where I is the moment of inertia and W is the angular velocity. Let's represent the gyroscopic precession. So let's say you have a gyro here within a vertical plane. Okay, so it is in the vertical direction, and this gyro is rotating like this, correct? Let us draw it more aesthetically. So the torque of rotation would be in this direction, correct? And the gyroscopic precession is the force that is generated by the rotation movement, okay? And it would be pushing sideways. So let's say this is the axis of rotation around which this gyro is revolving. This is where the precession force is created. That would be the precession force, okay? That would be the gyroscopic precession. That would be pushing the wheel or the gyro in this case sideways. And oh, by the way, as for the direction of this precession force, this is how you get the direction. So in this case, let's say the wheel is turning like this, okay? You can imagine it as a screwdriver, okay? So when you have a wheel turning like this, and it is a screwdriver, it would be removing a screw from the wall, right? And it would be in this direction. Meanwhile, if it is rotating clockwise, So it would be driving the screw on the inside the wall, and the direction or the heading of the precession force in such case would be in that way, okay, for the clockwise motion of the gyro. Common gyro failures, you have vacuum pump failure, which would lead to the loss of the momentum of the gyro because it would be driven by the pump itself, by the vacuum pump, so as to force it to rotate. Okay, that would be the main force, which is caused by the differential pressure. This is what would be driving the gyro to make it rotate. Electrical power loss, because you would have gyro systems that would be driven by the power, by electrical power itself. That would lead to gyro failure. Bearing wear, so like some of the mechanisms of the gyro would wear out, especially the transmission between the gyro mechanism and the needle. Okay, all of these gears on the inside of the instrument would wear out for some reason. That would lead to the instrument breaking. Failure symptoms, slow drift. So one of the symptoms would be that the indication would be lagging behind the actual current value, whether for the airspeed or the altitude or the VSI. Sudden tumble, so it would suddenly shake or it would suddenly drift from one value to another. It won't be gradual. So that would be a symptom of an erroneous reading and a malfunction within the instrument, especially within the gyro. And erratic indications. And by the way, it's not necessarily the gyro itself, but the transmission between the gyro and the needle, the indication needle. And erratic indications or values that won't make any sense. Specific instrument failures. Okay, let's talk at first about the attitude indicator. So the attitude indicator may roll or pitch without aircraft input. Basically, the gyro would always be maintaining a horizontal direction. It would remain in the horizontal plane. Meanwhile, the aircraft itself would be rotating around that gyro. So it would be the reference for the horizontal horizon, correct? Now, as for the banking index, that would be performed by the gimbal rotation and also the pitching up and down by the horizon reference arm, okay? That would be actually, I'm sorry, the horizon reference arm would be fixed at the horizon, at the horizontal plane, but you would have pitch gimbal rotating around it that would move this indicator up and down. You have the gyro that would maintain the horizontal plane stable. So when you have any of these parts breaking somehow, that would lead to a roll of the attitude indicator or a pitch that is not actually due to a legitimate aircraft input, but due to a malfunction or a part breaking within the aircraft. For example, when the aircraft is climbing, what will happen is that this disc here would be lowered so as to indicate this horizontal arm reference being placed or being in movement on the upper half of the disc, which is the blue part, which means that you are climbing vertically, okay? You are ascending in altitude, okay? You're pitching up, not necessarily climbing or increasing in altitude, but the nose is pitched up. Meanwhile, if the aircraft is pitched down, what will happen is that this arm, or not the arm is always fixed, but however, the brown side would be going upwards, okay? Also, as for the bank roll, so what you'd have is the aircraft banking around this horizontal arm, which again is the reference axis or the reference arm within a reference horizontal plane. Faults in the heading indicator. At first, how does the heading indicator work? So you have a directional gyro, that would be the gyro rotating in the vertical plane. This should be always rigid. This is why the importance of the rigidity, which means that it should not be affected by the gyroscopic precession, but still it will start drifting gradually from the course, okay, that was the correct one, that would be, by the way, derived from the compass, okay? So it would always be synchronized by the compass, the magnetic compass. However, it provides stability, unlike the magnetic compass that would start budging left and right, okay? It's not stable, the other one. However, the directional gyro is stable. It can provide a correct, like a stable heading without any budging, without any rotation sideways. But still, it is prone to faults such as gradual drift during its operation, and this is due again to the gyroscopic precession. Other faults can be due to the mechanism on the inside. Something might break and the wheel itself would start moving sideways, which would start manifesting as wrong indications, wrong values for the heading. Let's examine the anatomy of the heading indicator a little bit. So how does it work? You have the directional gyro here rotating in the vertical plane around this axis. That would be the gimbal. Now, as it rotates, it is also moving the gimbal. You have the gimbal rotation here, this disc, which is connected as a gear system. You have the main drive gear that would rotate another gear. In its turn, the second gear is connected to a compass card gear, which would revolve the directional card, okay? And this is what would give you your current heading in reference to this vertical, like this airplane, this arrow, so to speak. This would give you your current heading at the moment. And this, of course, would be the adjustment knob for correction, okay? And the adjustment gears. Now, as a side note, due to drifting that is caused by the gyroscopic precession, you would need to readjust that rotation, and usually it is done automatically in modern aircraft. There would be a synchronicity, or like a synchronization between the magnetic compass and the directional gyro, because the directional gyro actually takes the correct heading from the magnetic compass. But the drawback with the second is that it's not stable. It is prone to turning and rotation, so that would cause it to move, to sway between two different points, okay? Which would not be accurate, and it cannot be reliable so as to be used, I'm talking about the magnetic compass, so as to be used as a reference by the autopilot. Third coordinator or slip coordinator. This instrument may suffer from a loss of weight information, okay? So let's, at the beginning, try to understand how does it work to begin with. So you would have an inclined disc, okay, an inclined gyro, which is around 30 degrees inclined sideways. So it's not either in the vertical plane or the horizontal plane. It's rotating in both, which gives it the ability to measure both the turn, okay, like the banking, the roll, but at the same time the slip, which means that when the aircraft is skidding, is not rotating like this normally, but it's slipping sideways. And this is, by the way, would be detected by the gyroscopic precession itself. In such case, it would be measured by that mechanism. Okay, so you have the gimbal, the gyro rotation, which is again inclined 30 degrees sideways, the gimbal rotation, inclinometer, standard rate turn index, and canted gyro. Okay? Since it's not clearly stated here as to what types of failures should we expect in this instrument when it comes to the turn forward / slip coordinator, or what types of things can go wrong with the mechanism, we're going to try to assess that by looking simply at the instrument and how does it work. By looking at the mechanism, you see the gyro is inclined 30 degrees sideways, so it's neither revolving in the vertical plane nor in the horizontal plane. And this is on purpose so as to detect both the slip and the turn. Okay? Now, for the slip, this ball here would be moving to the side when the aircraft is yawing without turning. Okay? When it's slipping, this is called a slip movement. As to the turn angle or the rate of turn, it would be measured or detected by this handle here, okay, so which rotates as the gyro moves. It is connected to the gyro. So when any of these mechanisms is damaged, okay, the turn won't be indicated. So you would lose the rate of turn and the slip due to a damage of the mechanism of the gyro or the connecting gimbals or other things like other gears that are connected to them, so as to transmit this info to make the disc here, the indicating disc of the turn, rotating one way or another. Partial panel flying techniques. Definition: partial panel flying refers to controlling the aircraft safely with one or more primary instruments failed, which means that you cannot rely on these failed instruments. You have to be able to rely on the alternatives or whatever is still existing in order to keep flying the airplane safely. Control and performance method. This technique emphasizes pitch control via airspeed or power. Okay, correct? Bank control via turn coordinator and compass. So you would bank the aircraft based on alternative instruments such as the turn coordinator and the compass. And power control via engine instruments. So you would control the power via the engine instruments. Okay, this is how you would stabilize the aircraft and try to maintain a specific flying speed, specific attitude, specific turn, etc. Scan adaptation. Instrument scan must be restructured, so you need to prioritize reliable instruments that are actually working. Ignore the failed instruments because they are no longer reliable. You can no longer get significant information from them, and use cross-checking to validate information. So we need to verify what we're reading or what we're getting from the aircraft by cross-checking the available instruments that are still working, that are still operating normally. Limitations: partial panel flight increases, so the workload would increase. Risk of spatial disorientation increases, especially when you have lost something like the attitude indicator, and the dependency would be on the training proficiency. Okay, so it would be much harder to control the aircraft, especially during night, especially if you're flying in the dark or in the clouds. At the end of this chapter, flight instrument failures often present misleading information rather than obvious loss. Understanding failures, signatures, pressure relationships, and gyro behavior allows pilots to quickly identify unreliable instruments, to take them out of the equation. Effective partial panel techniques and disciplined cross-checking are essential to maintaining control and preventing loss of control accidents. Chapter or Module 8, Flight Control and Trim Emergencies. Overview: flight control emergencies involve partial or total loss of the pilot's ability to command aircraft attitude or trajectory. Unlike engine failures, control failures directly threaten aircraft controllability, like a rudder hard-over situation. Primary effects include increased control forces, like when you have rudder bent on one side, you need to fight against it. Reduced maneuverability, so loss, almost like a partial loss of control, and difficulty maintaining stable flight. Early recognition and correct technique are critical to avoid loss of control. Control stiffness or restriction. Definition and causes to control stiffness, which means that you're trying, let's say, to roll the aircraft to one side and it's not moving. It seems to be very heavy. The controls are heavy. It seems to be much harder to control. Or stiffness can imply that you're trying to, let's say, turn the rudder and it's so sluggish, or it's so like it requires much more force from you as a captain in order to turn the rudder, okay, in order to apply that kind of control. Or restriction, something like, for example, has been locked out and you can no longer control it, like you lost the control on one or two sides of the aircraft. You lost the control, I don't know, on like the elevator seemed to be no longer moving, or the ailerons due to, for example, a hydraulic problem. Definition and causes. Control stiffness refers to abnormally high force required to move flight controls, while restriction refers to limited or blocked control travel. So you're no longer gaining access into moving the elevator, for example. Common causes would be control surface icing. So due to the icing, the control is stuck on one position. Foreign object interference, so something had entered between, the controller, let's say, or like the control surface and the wing itself. Mechanical deformation or damage, so like a twisting within the mechanism of the rudder or the elevators, like the hydraulic device, okay, is jammed on one side, or something had snapped, or leak of the hydraulic fluid. And finally, hydraulic pressure loss. Actually, yeah, that would be the one in powered systems. So you have a loss of hydraulic pressure due to the loss of the mechanism of the hydraulics themselves, or a leakage in the hydraulic fluid. Aerodynamic control forces. The control force is proportional to dynamic pressure, which is Q is equal to 1/2 rho V squared. And let me explain. This has to do to the pressure which is the static pressure, by the way, the pressure that is required to be pushing against the air that is hitting the control surface versus the aerodynamic pressure. So the ram air that creates a dynamic pressure, which is given by Q is equal to 1/2 rho V squared, becomes a static pressure against the wing surface itself, the control surface itself. And that static pressure, okay, is equal to F divided by the surface, okay? So you need a counter force that would be opposite to that force created by the pressure in order to move the surface itself. So to give you an insight again, but at first let us read. So as airspeed increases, the dynamic pressure increases, which is equal to 1/2 rho V squared due to an exponential rise of the velocity, which is squared. So the control forces increase significantly as a result, which is aggravating stiffness problems, okay? It would be so heavy on the arm of the pilot in order to move, or on the leg, if we're talking about the rudder. Let's establish the relationship between the force required to move the control and the dynamic pressure. So, at first, the dynamic pressure, which is the pressure of the moving air attacking the surface of the control area, let's say the rudder, okay? This dynamic pressure is given by the formula Q equal to 1/2 rho V squared. That would turn into a static pressure, which is equal to F over area, F over S, the surface of this control surface, okay? This control part of the wing. So this same force that is pressing like this, you would need to counter it with the same force being applied by the pilot. So this is exactly the force required to move this control surface when it's being countered by the ram air, the dynamic pressure, okay? So the force is equal to F equal, take this formula, okay, S multiplied by Q, or in other words, Q is 1/2 rho V squared, so it is equal to S times 1/2 rho V squared, okay? So it would be, let me erase a little bit here to make it more neat. So the force required to move the control surface would be given by 1/2 rho V squared multiplied by S, which is the surface of this control part, this wing part. In this example here, it would be the rudder, okay? Now, notice something. As the velocity increases, what happens is that the force required to move the control surface would increase. But not only the airspeed, also you need to add another factor, which is the density. Now, what does affect the density? The altitude, because as you descend, especially during emergency landing, the pressure against this control surface would increase due to the rise of the density. Okay, the density at sea level would be much higher than that at 15,000 feet. Okay, more than that, the velocity, as it increases also, it can put more pressure and it would require more force for the pilot to move or to budge the control surface. Operational considerations: pilots should reduce airspeed to lower control forces that are required. This is why you would reduce the airflow or the airspeed by reducing the engine power so that you can provide more controllability for the surface. Avoid abrupt maneuvers so as to avoid ripping off the control or like overstressing it and the control surface. When you have, for example, a rudder hard over for some reason, it might be completely turned off or like torn off. The control might be completely turned off if it still has some controllability, or the rudder itself might be completely torn off the vertical stabilizer specifically. And use trim to relieve sustained forces, so you trim like the right side in order to alleviate for the left rudder hard over, for example. Left rudder hard over, actually you'd be trimming the left side aileron in a way that it would be turning right, and also manipulating the asymmetric thrust so as to make the engine power differential release also or relieve the pilots from having to apply the forces all the time in order to stabilize the aircraft. Trim runaway and trim failure. Trim systems overview. Okay, trim systems reduce continuous control force by adjusting aerodynamic balance surfaces, by moving a small part of the control itself that would be like adjusted in order to stabilize the aircraft. Trim force balance can be expressed as the sum of moments should be equal to zero so as to guarantee a stabilized flight. Okay, for example, while maintaining a leveled flight, where sigma m, which is the sum of the pitching moments, should be equal to zero. Let's talk about trim runaway. Trim runaway is an uncommanded continuous trim movement due to electrical faults or stuck trim switches which keep moving the trim control, or autopilot malfunctions. So the autopilot is basing his own actions on falsified readings, or it's not correctly performing. Okay, at the end of the day, it's a computer prone to errors. Pitching moment generated by trim runaway is given by m trim is equal to the force of trim multiplied by distance. By the way, any rotation or any revolving motion, it has a moment, and this moment is equal to the force being applied perpendicular to the radius of the rotation times the distance from that force being applied and the axis of rotation. Uncorrected trim runaway can exceed pilot control authority, and this is when the pilot can actually lose the control. Trim failure. What are the consequences of a failure of a trim, whether on the rudder or the elevator or the ailerons? All of the control surfaces have a trim to them. So the result would be loss of trim effectiveness, requirement for sustained control pressure, so you would need more force, it would be more straining and more stressing on the pilot because he would need to maintain the control pressure in order to stabilize the flight, and increased fatigue that would be on the pilot and the crew. Proper technique involves manual trimming, airspeed control, controlling the airspeed, and load management. For example, you have a trim hard over to one side on the rudder. Okay, you would need to adjust or readjust the asymmetric thrust so as to give, for example, let's say the trim is to the left, so it is yawing the aircraft to the left. You need to increase the engine power to the right and reduce that to, you need to increase the engine power to the left, reduce that to the right, so as to provide an asymmetric thrust that would counter the yawing motion, the yawing force that is turning the aircraft, yawing the aircraft to the left. Okay, so as you increase the engine power to the left and reduce that to the right, you would counter that force pushing the aircraft sideways, leftwise. Control surface disconnects. Okay, what are the different natures of disconnects? Control surface disconnects occur when pilot input is no longer transmitted to the control surface. One of the reasons would be the leak of the hydraulic liquid, which is required for the transmission of that action that is applied by the pilot all the way to the control surface, or breaking of the line, like the rope, the rod of control. This is mainly in smaller aircraft sizes, or loss of an actuator, for example, which transform the electrical power that is transmitted from the computer in such case to a mechanical power to move the rudders or different controls. Okay, the rudder or different controls. You usually have only one rudder. So, as an example, elevator cable failure, like it snapped, for instance, for some reason. Rudder linkage separation, so the linkage of the rudder rod, the control rod of the rudder, and the mechanism had separated from the control of the pilot or the hydraulics. Hydraulic actuator disconnects, as we mentioned moments ago. Effects on aircraft dynamics. Loss of a control surface reduces available control moments. Okay, so the available moments would become less than the moments of force required to move the control. This limits maneuverability or maneuverable capability and may prevent certain attitudes or configurations to be attained. Compensating techniques. Pilots may compensate using remaining control surfaces. For example, the ailerons, power changes to induce pitch or yaw, which happened many times before. So, in order to induce pitch or yaw, you would start yawing the aircraft by applying asymmetric thrust, as we mentioned before. So, let's say you want to yaw to the left, okay? So, you want to move or push the aircraft to the left or to the right. Let's say to the left at first. You'd increase the engine power to the right and reduce that of the left engine. So this way, the aircraft would start yawing to the left. Or you would apply the ailerons. So by the differential of, you see, the weight of the aircraft would be, as you roll the aircraft, the weight would become two composites, an horizontal composite, horizontal vector or component of the vector, and a vertical vector, which is 90 degrees with the airframe, okay? Because the weight vector is always vertical. So the horizontal component would start moving the aircraft sideways, all right? And trim adjustments. We can also play with the trims in order to compensate for a control loss. Manual reversion or degraded control loss. What are manual reversions? Okay, and degraded controls. So manual reversion occurs when power-the-flight controls revert to direct mechanical control. So instead of being powered, they revert to the mechanical control so as to provide more controllability to the pilot. This significantly increases control forces. Why? Because you are fighting against the aircraft itself in such case. So you need to be pushing against the forces that are acting on the wing surfaces and the control surfaces specifically. And we mentioned that before. When you have especially a high airspeed and a higher density at at lower altitudes, this would incur a higher dynamic pressure that would reflect as a higher static pressure against the moving part of the wing, and you need to counter that force of that pressure with the same force, with an equivalent force, which would be so straining for the pilot with limited physical capabilities. Okay, so reduced control authority also. So you would no longer have full control over the different surfaces, and loss of artificial feel. So in other words, instead of the aircraft controlling its own moving parts, its own control surfaces via the actuators, via the hydraulics, you would be in direct charge for moving these parts that have become so much heavier on your own physical power, okay? Or physical strength. Control force relationship, the force of the pilot is directly or inversely proportional to the assistance of or coming from a hydraulic or electrical force, a hydraulic or an electrical system. Degraded control laws. In fly-by-wire aircraft, degraded control laws may replace normal laws following failures. Let's at first start with defining what is a fly-by-wire aircraft. How does it work? In fly-by-wire systems, you have the different controls within the cockpit are relayed to a computer, and the computer would analyze the generated current as you move the rudder pedal, as you move the yoke, for example, or the trim. It would analyze the current being generated by these movements, by the pressure being applied to these different controls, and it would analyze it, amplify it. Okay, the computer actually would analyze it, then it would send it to an actuator. Of course, it would be amplified, and then the actuator would convert the electrical energy to a mechanical energy and move in its turn the elevator, the rudder, the trim, etc. Okay, but it is not the pilot directly moving the control, but rather the actuator is the one that is applying the mechanical motion for, to turn the rudder or the elevator or different controls of the airplane. So the changes would include loss of envelope protections, direct control surface response. Okay, so the surface is no longer being controlled by the actuator, but rather by the pilot himself. So the surface would immediately or directly be responding to the force being applied by the pilot, which would increase the pilot workload and it would place more pressure on the pilot. Now, loss of envelope protection means that the limitations concerning the movement of different controls would be lifted up because it was controlled by the computer and analyzed by the computer. Now, on your own, you need to be deciding how much pressure to apply on different controls to try as much as you can to fly safely. Okay, so the system prioritizes controllability over optimization. This is why it is more important to have controllability over the aircraft than way more than optimization. Landing with limited controls. Landing strategy would be higher approach speeds. So in such case, you cannot deploy the flaps, for example. So this would be one of the results of not having the flaps during the landing. Reduce configuration changes. So multiple things would be out. You can no longer, like, for example, since we're talking about controls, for example, if you had lost the hydraulics, also you can no longer control the rudder and the ailerons so as to align the aircraft with the runway. So you would need to use instead the engine power, the asymmetric thrust again, in order to yaw the aircraft right and left so as to, and to turn it right and left so as to align with the runway. And extended final approach, so you would need a longer runway while taking care of the stall margin or paying attention that the velocity of approach should be greater than or equal to at least 1.3 the velocity of stall or stall velocity, because in such case you would need more speed so as to compensate to the lift that you had lost, the extra lift that was provided by the flaps that you no longer have. Control substitution. When controls are limited, pilots may use the following. Power for pitch control, which we've mentioned before. So you would increase the power in order to pitch the aircraft up and decrease it in order to pitch down so as to lower the nose as much as possible in preparation for the landing. Bank and go for descent rate. In order to increase the descent rate, the aircraft needs to be banked sideways, and this happened, by the way, in the Gimli glider air incident over Canada, so where the pilot actually had to increase the descent rate in order to avoid overshooting the runway, which was a small abandoned runway, by the way. So he started slipping the aircraft by increasing the bank angle in order to lose as much altitude as possible, and differential thrust with multi-engine aircraft, so which is the asymmetric thrust. So you increase on one side, decrease on the other in order to yaw or turn the aircraft using the engines alone. And especially during the landing, so as to attempt to align the aircraft with the runway before touchdown. Risk management. Key risks include over controlling the aircraft, so over applying one control or another, over yawing, structural overload, and it happened, by the way, during takeoff. In one of the incidents, I think it was a DC-9 aircraft over New York, and it crashed in Queens. This is back in 1990 or something like that. What happened is that due to the over pressure, okay, like the pilot was over applying the rudder because he was overly concerned of the wake turbulence, so he did not want that the wake turbulence overturn the aircraft. So it was like a mystically ingrained thought, which was actually not accurate. So after applying the rudder multiple times, the turbulence became so high. He actually ended up creating more turbulence and overstressing the rudder and the vertical stabilizer that ended up being torn off the airplane altogether, and it went down in a tailspin and crashed in Queens. Okay, so that would be the consequences of structural overload, tearing off the controls or any other surface of the wing. Runway excursion. So you cannot overshoot the runway. You need to land as short as possible, and in emergency landings, you would need the longer runways. Early decision making and conservative techniques greatly improve outcomes. So flight control and trim emergencies challenge the pilot's ability to physically control the aircraft. Understanding control force relationships, trim behavior, and system degradation allows pilots to adapt techniques and preserve controllability. Successful outcomes depend on airspeed management, smooth inputs, disciplined decision making, and thoughtful decision making, even under pressure and stress. Chapter 9 or Module 9, Pressurization and Environmental Emergencies. Pressurization and environmental control systems are critical to aircraft safety, particularly at high altitudes where atmospheric conditions are not favorable for humans. So you would need higher pressure, that's why the pressurization within the cabin, and a larger amount of oxygen, which implies a higher density of the air in order to be able to survive within the aircraft. Failures in these systems can lead to hypoxia, which is suffocation from the lack of oxygen, okay? Decompression events, smoke or fire hazards, and require immediate and correct pilot response. Hypoxia recognition. Hypoxia is a condition in which the body tissues do not receive adequate oxygen to maintain normal physiological function. In aviation, hypoxia typically occurs due to insufficient amount of oxygen or lower air pressure, which can also conduce to the same results. So, hypoxia typically occurs due to a lack of oxygen, partial pressure at altitude, or failure of the oxygen delivery systems. Types of hypoxia. Let's start with hypoxic hypoxia, which is simply the reduced oxygen pressure at altitude with the rise or increase of altitude because of a lower density of the air, which also leads to a lower amount of oxygen being inhaled. Hypemic hypoxia, which is the reduced oxygen carrying capacity of blood due to the existence of carbon monoxide poisoning. So the same blood cells would be carrying carbon monoxide instead of oxygen, which would also lead to suffocation. So the third is the stagnant hypoxia, where you have inadequate blood circulation due to a low blood pressure, and histotoxic hypoxia, where cells are unable to utilize the oxygen. That would be more physiological. Physiological basis, atmospheric pressure decreases exponentially with altitude, reducing the partial pressure of oxygen, which would be like that. This would be the drop of oxygen. So the pressure of oxygen would be equal to the force, okay, or the fraction of oxygen in the air multiplied by the atmospheric pressure, which is the ambient or the current atmospheric pressure existing at a designated altitude. So the partial pressure of oxygen is equal to the fraction of oxygen in the air, the percentage of oxygen in the air, which would be around 20%, multiplied by the atmospheric pressure. As altitude increases, the atmospheric pressure decreases, which would lead to a starvation or a deficient amount of oxygen being available to be inhaled. Insufficient oxygen diffusion into the bloodstream, which can lead to asphyxiation. Symptoms of hypoxia. Early, okay, the early symptoms would be impaired judgment because the focus of a person would drop due to the lack of oxygen needed so that he can be at high alert and at high mental processing of what's happening. Euphoria, which would be like the alcohol effect, by the way. So he would become euphoric and dizzy and illusional somewhat. And tunnel vision, so he can only observe what's right in front of him, okay? He can no longer see the bigger picture of things. Second, the intermediate stage, he would get headache. So if it's not like gradual, if it's intermediate, headache, dizziness, and cyanosis. And if it's severe, he would have loss of consciousness, so he would black out, seizures, and eventually death. Hypoxia is especially dangerous because symptoms may not be immediately recognized. He might be blacking out gradually. Okay? So it wouldn't be immediately recognized by the affected crew member. As a side note, cyanosis is when you have a bluish color of the skin due to the lack or deficiency of the oxygen. So a person's skin would start becoming blue due to a deficiency or a lack of oxygen. Now, dizziness is when someone would start to lose his focus, his concentration, as if he's at the verge of falling asleep. And seizures are symptoms like the stroke, okay, like those of a stroke. Rapid versus slow decompression. Decompression occurs when cabin pressure is lost due to a structural failure like a puncture within the airframe, seal leaks, which would make the oxygen or the pressurized air leak outside of the aircraft due to the differential of the pressure between inside the cabin and the outside, which is the ambient atmosphere. At high altitudes, it would be a very low pressure in comparison, or system malfunction, which is the pressurization compressor. Slow decompression occurs gradually and may go unnoticed initially. Indicators include cabin altitude warning within the cockpit, gradual onset of hypoxia symptoms, so the lack of oxygen would start becoming more prominent, and fogging of windows. As for rapid decompression, it is usually caused by a sudden structural failure or sudden extreme damage within the airframe, such as the bullet puncturing a hole within the airframe or sudden explosion, etc. Okay? It is characterized by a swift loss of cabin pressure, which would come about suddenly, not gradually, typically within seconds. Effects include explosive airflow, fog formation on the windows due to rapid cooling within the cabin, potential structural damage. So this sudden decompression would rip out the body of the airframe, and in some incidents, it had taken the entire upper cap of the aircraft, like the upper compartment, the one covering the passengers, and immediate hypoxia risk, which would be the sudden loss of oxygen and sudden asphyxiation. Let's talk about the gas-law relationship. So rapid decompression follows Boyle's law. Okay, Boyle Marriott, by the way, his name. He did a research on gas pressure and volume, the relationship between both. So P1 V1 is equal to P2 V2, meaning that the change in pressure and volume is constant. A sudden drop in pressure, P2 being less than P1, causes trapped gas to expand rapidly. Okay, so as the pressure increases, the volume decreases and vice versa, which may result in physical injury, e.g. barotrauma. Okay, trauma because of the sudden pressure differentiation, okay, or differential. Smoke, fumes, and fire in the cockpit or cabin. Smoke and fire represent some of the most time-critical emergencies in aviation. The sources would be electrical faults, electrical surges, overconsumption, like a high load on the power being generated, and this high load cannot be carried using like the electrical wires that are being implemented. So they were never designed to carry this overload, so they start heating up, and even the insulants would start melting, causing a smoke and eventually causing a fire, if not attended for. Bleed air contamination, okay, lithium battery, so bleed air contamination, which is the air from inside the engine would bleed inside from outside of the engine inside the cabin. Lithium battery thermal runaway also, and engine or APU fires, so fire within the engine backfire, for example, or APU, which is the auxiliary power unit, used as a backup in order to start up the engine in case the pilot had an engine flame out. Hazards like toxic gases, e.g. carbon monoxide, reduced visibility, structural damage, or crew incapacitation. Those would be the hazards, okay? Toxic gases being released in the cabin, reduced visibility due to the fogging, due to the smoke, basically. Structural damage, so the fire can eat up the undercarriage, can eat up the engine based on, like, it depends on where the fire had started and how long it went undetected, which would escalate the problem. And finally, crew incapacitation due to the starvation of, from oxygen, or like the smoke would overwhelm the crew, which would lead also to smoke poisoning, or even the fire itself would eat up, like it can unfortunately get to the crew. So, carbon monoxide consideration. Carbon monoxide binds with hemoglobin approximately 200 times more readily than oxygen. The hemoglobin is actually the red blood cell, which carries the oxygen to different organs within the body. And it also, so it carries the oxygen in, being pumped by the heart, and then it carries the carbon monoxide out through the transpiration, through the exhale, okay? So, since the carbon monoxide, actually it is the CO2, the carbon dioxide, it is carried, the thing that is carried outside of the body. But the carbon monoxide can attach to the blood cells much more, like 200 times more than the oxygen, which would lead to the asphyxiation due to that fact. So HB, or hemoglobin plus CO, it would give you HbCO. This significantly reduces oxygen transport capacity, leading to hypemic hypoxia, which is the monoxide poisoning. Oxygen system operation and failures. Aircraft oxygen systems provide supplemental oxygen during pressurization failures or high altitude operations. Okay, types of oxygen systems. The gaseous oxygen systems, okay, within the cabin. Chemical oxygen generators, which are also like when you have the drop of the mask within the cabin. That would be a chemically generated oxygen as a backup, and liquid oxygen or LOX systems. The oxygen flow principles. Oxygen delivery depends on cabin altitude and system design. The required oxygen partial pressure must exceed the minimum physiological threshold. So, the pressure of O2 alveolar should be greater than or equal to 60 millimeter Hg, okay, millimeter, which is mercury, okay, mercury pressure. Failure modes include mask or regulator malfunction. So the mask would malfunction, or the chemical regulator, oxygen bottle depletion, or valve or linear leaks, okay, leaks within the valve or linear leaks. Emergency descent procedures. An emergency descent is executed to rapidly reduce altitude to a level where breathable air is available without the need for supplemental oxygen, because at higher altitudes the density is very low and the oxygen cannot be, dense enough to be inhaled, to be breathed by people. So the objectives would be to restore safe oxygen levels. This would be the main reason behind emergency descent during a depressurization of the cabin, prevent crew incapacitation and asphyxiation, okay? Third, minimize structural and physiological stress against the aircraft due to this differential of pressure between the cabin, which would be leaking. However, it may not necessarily, and it rarely loses the entire pressure. So this leak is pinching through the airframe, which implicates more structural damage as the flight keeps carrying on. Descent performance. Rate of descent, or ROD, can be approximated by ROD is equal to V, which is the true airspeed or velocity, multiplied by sine gamma, which is the descent flight angle. Okay? Descent flight angle. So, high drag configurations, for example, speed brakes, landing gear, if approved, increase gamma, which is the descent flight path angle, allowing faster altitude drop or altitude loss. To give an example, let's say you have an airspeed of 170 knots. This is the airspeed, and gamma, which is the rate, not the rate, I'm sorry, the angle of descent flight path angle. This is the aircraft here, okay? It is descending by 30 degrees, let's say, okay? So delta equal 30 degrees. The airspeed is equal to 170 knots. So the rate of descent would be given by airspeed is 170 knots. We're considering that this is the true airspeed, multiplied by sine 30 degrees, which is 1 over 2, 1/2. So that would give us 170 over 2. So 16, okay, 85. It would be 85 knots. Okay, that would be the rate of descent. Okay, 85 knots. Yeah, knots per second. Okay, 85 knots per second. So 170 over 2. Typical emergency descent actions. At first, you need to have oxygen masks deployed and on. Establish maximum safe descent, meaning you need to descend as quickly as possible while maintaining safety. So it should not be like a comet ride. Thrust needs to be set to idle so as to make the aircraft fall on its own gravity gradually. Okay, not fall, but descend on its own gravity. Speed brakes deploy in order to reduce the speed so as to avoid having an overspeed indication, which can tear, like at risk of implicating or placing more stress, structural stress on the entire aircraft. So that's why it is important. Descent to safe altitude, typically 10,000 feet. Prompt and disciplined execution of emergency descent procedures is essential to prevent loss of aircraft control or crew consciousness. Module or Chapter 10, Landing Gear and Brake Failures. The landing gear and braking systems are among the most critical aircraft subsystems during ground operations, definitely. And also, especially landing phases. Failures within these systems can significantly compromise directional control and the stopping distance once the aircraft touches down. Also, it can affect or like it can impact structural integrity when you have one of the landing gears snapping, for example. And you would lose control on the ground because you need the wheels to maneuver the aircraft once it touches down in order to steer it. Okay? So, stopping distance, structural integrity, requiring immediate diagnosis and precise pilot response. Gear indication failures. Landing gear indication failures occur when cockpit indications do not correctly reflect the actual position of the landing gear. As an example, let's say you are running the checklist for landing and you had deployed the landing gear, but it did not fully extend. You see, once the landing gear goes into full extension, it would like kind of touch a sensor, if it's a contact sensor, or if it is like a distance detection sensor that would detect that the landing gear is actually in place. So once this happens, the green lights would appear on the cockpit indicating that the landing gear is fully extended, which is proper during the landing. However, in case you had red or like yellow, orange indications, it means that they are not fully extended and there's something wrong with the landing gear. Or during the transition, by the way, they would be lit orange. So during the full transition from like retracted to fully extended. Common causes: faulty proximity sensors or squat switches. So you would have the sensors that might be wrong, okay, that might be defected, or the squat switches. Wiring or power supply failures. So because you need a power, okay, you need power in order to run the motors to extend the gears. Indicator bulb or display malfunction. It can be the displays or the indicator bulb itself within the cockpit that is faulty, or like for example due to a short circuit. Or hydraulic or mechanical misalignment, which means that the hydraulic pressure was not powerful enough due to misalignment, so it prevented the gear from fully extending. The failure characteristics: a gear indication failure may present as unsafe or disagree warning, okay, like an orange indicator on the landing gear indicator. Partial gear indication, which means that it had not fully extended. No gear status indication, so it did not extend in the first place. It is critical to distinguish between an indication failure and an actual gear failure, gear extension failure to be more accurate. So we need to try to assess whether it is a problem with the indicating light, with the monitoring system, with the sensor, okay, or whether it is the landing gear itself, it did not fully extend, which is the most common problem, by the way, in the landing system. Verification techniques: alternate gear indication system. So you would look at other indicators. Visual confirmation by mirrors, external observer, like you can contact the ATC to look after you, or chase aircraft. Another aircraft can report whether the landing gear has been extended or not. And the gear position lights and auto warnings, like the sound warnings would indicate whether the gear is fully deployed or not. Manual gear extension systems. Manual or alternate gear extension systems allow landing gear deployment in the event of hydraulic or electrical failure. So how does it work? You basically deploy the landing gear on its own weight. You let the gravity try to pull down the landing gear in such case. That would be conducted in an emergency condition. So operating principles. Manual extension systems typically rely on gravity, on the springs, the dampers, okay, and mechanical cables or cranks. So it can be at times manual, depending on the type of the aircraft. Once released, the gear free falls into position, okay, it would fall freely into position and is locked by aerodynamic forces themselves and also mechanical down locks, okay. Usually it would be the down lock when it is extended. The hydraulic pressure consideration. Hydraulic systems operate according to Pascal's law. So the pressure is given by the force divided by the area where this force is being applied. This is actually the definition of pressure. So P, which is the hydraulic pressure, is given by F, applied force, divided by piston area. Loss of pressure, so P going to zero necessitates manual gear deployment. The limitations: increased extension time, so it would take more time to deploy. Possible lack of positive gear down indication, so it may not fully lock so as to fire the indicator in the cockpit to confirm to you that it has been fully extended. And gear retraction may not be possible ever afterwards, okay? So going around the airport would be a little bit harder in such cases. Brake failures and brake fires. Braking system failures can result in reduced stopping capacity, directional control issues, so the aircraft can veer off the runway in some cases, or overheating due to the drag or the friction between the wheel, which is usually in such case the wheel, frame, metallic frame, and the runway itself. The brake failure causes would be hydraulic fluid loss due to a leak, for example, anti-skid system malfunctioning, and contaminated or worn brake pads. Also, the fourth possibility would be the brake valve failure, okay? The same valve that delivers the hydraulic pressure to the brake. In order to give you more insight, I've added some pictures or illustrations. So this would be the brake pad, just like the one you have in your own car. It works the same way. So it presses against, this disc, like the disc or the wheel disc, in order to brake the aircraft. And as for the brake valve failure, okay, that would be occurring to the valve that delivers the pressure of the fluid in order to move the braking system to press against the wheel to make the wheel of the aircraft stop and to eventually stop the entire aircraft. Braking force. The braking force is governed by friction given by Fb is equal to mu times n, with mu is the coefficient of friction and n is the normal force, okay, being applied by the aircraft on the ground, like the aircraft weight on wheels. Reduced friction or hydraulic pressure decreases the braking efficiency, all right, which can lead the aircraft to at times overshoot the runway or to eat more runway before full stop. The brake energy absorption, so this would be the kinetic energy of the aircraft, which is given by EK is equal to 1/2 mv square, with m being the mass of the aircraft and v the velocity on the ground. Okay, so kinetic energy would be converted to heat in order to brake the aircraft, to hold it. Excessive energy absorption can overheat the brakes, which can lead to an incendiary or fire event, okay? It can lead to brake fires. So brake fire hazards: tire explosion due to heat transfer or structural damage to landing gear components. Also hydraulic fluid ignition. Tire blowouts. A tire blowout is the sudden failure of an aircraft tire often during high-speed ground operations. Some of the common reason would be an excessive braking, excessive friction, which would cause excessive friction against the runway, or the tire has been old, it needed replacement, especially like another contributing factor would be a very hot weather that would cause an excessive inflation of the tire, okay, or during a very cold weather, an underinflation, etc. So the common causes, as listed here, overheating from excessive braking, as we mentioned, overinflation or underinflation, foreign object damage, that is another factor, FOD, so something running into the wheels or the wheel going over a sharp object on the runway, or structural fatigue, so the tires had worn out due to the factor of depreciation and needed to be replaced. Directional control effects. Loss of a tire can create asymmetric drag and rolling resistance. So it would be rolling on one side, but on the other it would be, scraping the runway. So due to the contact of metal against the ground or the runway instead of the wheel. So this would induce a high drag and causing a yawing motion to one side of the entire aircraft. Tire pressure relationship. So tire pressure varies with temperature according to the ideal gas law. P1 over T1 is equal to P2 over T2, where P is the tire pressure and T is the absolute temperature. Brake-induced heating can raise the tire pressure. This is where the problem would be. It can raise it beyond design limits. This can lead it to snap. Emergency landing techniques. Emergency landing aims to minimize aircraft damage, maximize occupant survival when normal landing is compromised or cannot be executed. Types of emergency landings: gear up, belly landing, which is usually done on a water surface, okay, because the gears would have a high resistance against water and the risk of tearing up the airframe. Partial gear landing, okay, actually, yeah. In fact, here they are talking about the gear emergency. So, yeah, in case the gear had not deployed, that would be one type of landing. Partial gear landing, so the gear had extended but not completely, not fully. Brakeless landing, so you have a loss of hydraulics. And off-airport landing, which means ditching on the sea. That would be the ditching part. Landing distance considerations. Stopping distance S can be approximated by the following formula. S is equal to V square over 2 mu G, where V is the touchdown speed, mu is the friction coefficient, runway friction coefficient, and G is the gravitational acceleration. Lower friction or brake failure significantly increases S, which is the range or the landing distance or stopping distance. Pilot techniques. First, use aerodynamic braking, which means the use of the air brakes or the spoilers. Deploy thrust reversers if available in order to immediately stop the aircraft upon touchdown. Maintain directional control using the rudder and nose wheel steering, which is this handle to the left of the pilot. Okay, that would be the nose wheel steering. Shut down engines prior to force stop if required. Proper execution of emergency landing procedures is essential to reduce structural damage on one hand and enhance the survivability during landing gear or brake system failures. Let's break down a little bit these different techniques. So, what do we mean by using aerodynamic braking? It is the deployment of the spoilers, which are the air brakes, that would increase drag in order to allow the aircraft to stop much faster than normal. So these would be the spoilers or the air brake system, which would deploy as a wall resisting the airflow in order to reduce the airspeed, actually the ground speed of the aircraft on the ground, to allow it to stop much more faster than normal. Reverse thrust is an action done on the engine level, which is by open up by opening up some caps that would reverse the propulsion of the engine, the thrust of the engine, to the front. Instead of going to the back and pushing the aircraft forward, it would push it backwards. This is why in some of the flights, the reverse thrust deploying in mid-flight had caused accidents, okay? It caused like disasters. Why? Because it halted the aircraft, leading to an immediate stall by disrupting the airflow, okay, due to the backward force pushing in the opposite direction of the flight direction. So this is usually deployed on the runway in order to decelerate the aircraft in an opportune time. And you have finally maintained directional control using rudder and nose wheel steering, which is as you move the rudder, for example, to the right, the aircraft would yaw to the left and vice versa. Now, as you apply a left rudder, the aircraft would move to the right. So this would keep or maintain the alignment of the aircraft at the center of the runway during landing, so as to guarantee it won't veer off the runway center or go completely off track of the runway, which becomes more dangerous. Now, shutting down the engines is very important prior to full stop. So, and especially during emergencies, in order to avoid fire breaking out within the cabin. So you need to place, and this is a visualization of the ECAS. So the EGT, both engines would be low, both oil pressure would be also it would go down as you shut off the engine, and the N1 and 2 rotations, of course, they would also roll back. They would indicate a rollback all the way to complete engine shutdown. Module or Chapter 11, Fire Emergencies. Fire emergencies represent one of the most critical and time-sensitive situations in aviation. So they are of utmost priority. Fires can rapidly compromise aircraft structural integrity, critical systems, and the livelihood of passengers as well. Okay, so immediate recognition by detection through the smoke detectors at first, because before fire you would have smoke, correct diagnosis of where the problem is coming from, and disciplined execution of procedures are essential to prevent catastrophic outcomes. Engine fire. So, engine fires may occur during ground operations or in flight and are typically associated with fuel, oil leak, or bleeding air system failures. Or, for example, when we talk about the airflow, so one of the rotating blades would break off, causing a backfire or an engine backfire due to an incomplete combustion of the fuel within the internal compartment of the engine. Common causes: fuel leaks or ruptured fuel lines, especially when the fuel is leaking next to the engine, which is very hot at the back near the exhaust. Oil system failures. So let's say you have an oil leak, especially inside the engine, which would be added to the mixture of the fuel air mix. Okay, so that third component would cause a flammability or a combustion above the normal temperatures, leading to a fire within the engine. Okay, that won't be contained easily. So this would lead to the engine not only backfiring, but it would erupt in flames, and it won't be even turned off that easily. It happened before, by the way. Also, hot section damage. Okay, of for example, hot section damage of the engine, bird strikes within the engine, or foreign object damage, so something flying into the engine, breaking a blade, disrupting the normal airflow within, so hence causing a fire on the inside and leading to an engine backfire. Fire characteristics: engine fires are sustained by the fire triangle, which is fuel, oxygen being fed into the engine, and the heat itself. Eliminating any of these elements can extinguish the fire. The combustion energy, which is the heat released during combustion, can be approximated by Q, which is the heat, total heat being released, is equal to M multiplied by Hc. Hc being the heat capacity or heat of combustion times the mass of the fuel that's being burned. What would be the procedure in case of an engine fire? So the fire suppression actions are the following. The thrust lever should be pulled back to idle. Fuel shut-off valve should be closed. That would be the checklist, the procedure. Engine fire handle being pulled in order to extinguish the fire within the engine. After choking, of course, the fuel flow and choking the oxygen being fed into the engine by pulling on the lever all the way to idle, which feeds the oxygen or the air into the engine system, and fire extinguisher bottle being discharged in order to make sure completely that the engine not only is shut off, but also it had the fire contained and extinguished. Electrical fire. This kind of fire would be the result of overheating due to wire overloading, for example, arcing or short circuits, where you would have a sparkle or sparkles going off from the positively charged wire, the positive pole, to the negative pole. This electrical surge would cause a fire. Okay, so that would be a problem in wiring, or electrical components wearing off, such as a resistor or something like that, wearing off or overheating, that would also cause a fire. Mainly the causes would be insulation degradation, which is the insulation between the plus and the minus wires, overloaded circuits, which happened before, by the way, on a DC9, I think, or DC10, I don't remember, where they had entertainment centers installed before each seat in the cabin, and these systems had consumed power like in a way that was overloading the wires. The wires were never designed to handle such power, okay, such current consumption. And to add more to the problem, they were like directly wired to the power distribution system without any installation of a circuit breaker. So there was no way to disconnect the system from the power bus. Okay, so this overloaded current would be transformed into heat since it cannot go through the wires normally. Third, faulty electrical equipment, okay, a fault in an electrical board, for example. And finally, moisture intrusion. That could be also a possible cause. Electrical heating. Resistive heating in electrical components follows Joule's law, where Q is equal to Ri square T. Ri square, by the way, is actually the power, electrical power multiplied by the time of exposure. That would give you the heat being generated. So Q, which is the heat generated, is equal to I, the current, square, multiplied by the resistance of the wire times the time, okay, multiplied by the time of exposure of the wire to that kind of current that's running through it. Excessive current or resistance increases the fire risk. Smoke characteristics. Electrical fires typically produce acrid odor, okay, dense gray or white smoke. So that would be one of the symptoms. And potential toxic gases due to the fact that you have insulators of plastic. The crew response would be oxygen masks should be placed on so that they would avoid being incapacitated due to the toxic fume potentially on board. Affected electrical buses should be isolated, and non-essential equipment should be turned off, just like we mentioned concerning the entertainment center within, I don't remember if it was a Boeing or a DC aircraft, McDonnell Douglas. Okay, they had no circuit breaker in order to disconnect the power from different TVs and different entertainment equipment that was being installed. Cabin and cargo fire. Cabin and cargo fires pose severe risks due to limited access and potential for rapid smoke propagation, because you have no direct access to these, like the undercarriage or the cabin. Okay, so cabin fire sources would be passenger electronic devices, as we mentioned before, the entertainment center, or like the mobile phones, which is very rare, but you would have a lithium battery today in your mobile, so that can cause also fire due to overheating or a malfunction within your own device, or a worn off battery. In flight entertainment systems, this is exactly what I was talking about moments ago: galley equipment and upholstery or insulation materials. Cargo fire characteristics. So, this would involve dangerous goods, lithium batteries that can inflame even when they are starved of oxygen at times, flammable liquids. This is why it's forbidden to bring liquids on board. Cargo compartments are typically inaccessible during flight, making detection and suppression critical. Okay, but they are usually starved from oxygen so as to prevent any fire from developing. Smoke propagation. Smoke movement is influenced by pressure and airflow gradients. Okay, so M, the mass is equal to rho AV, which is rho being the air density, A, the flow area, and V is the airflow velocity. That would give you the mass flow rate of smoke, which is, by the way, AV is actually the volumetric flow rate, which is the cross-sectional area of propagation times the velocity of the airflow, multiplied by the density. It would give you the mass flow rate in kilograms. Fire detection system failures. Fire detection systems provide early warning of fire conditions using temperature by the heat sensors, such as the heat sensitive resistors, smoke by the smoke sensor, which uses photodiode as a detector. So when the light being emitted by the LED lamp against the photodiode is blocked, this is where it detects that there's a fire. At times it can be, like dust confused as a smoke that can trigger the alarm, by the way, or gas sensors. The detection methods: thermal loop detectors using thermal resistance, optical smoke detectors, which what we've mentioned moments ago, by having a LED lamp against a photodiode, which is sensitive to light, by the way. So the value of the resistance would change based on the light flow or flux that it is being exposed to. So when the light flux is blocked, this would cause a short circuit or an open circuit, triggering the alarm for smoke detection. And gas-based detectors, so detection of specific gas based on other types of sensors, okay, that would detect the change of the capacitance, for example, based on the type of gas that's going through the capacitor armatures plus and minus, where the magnetic field is being held. Now, concerning the thermal loop detectors, by the way, so this is how they work. You would have a resistance that is sensitive to heat. Actually, it is made of a conductive material that dilates due to the existence of a hot temperature and contracts when there is low temperature. By dilating, what happens is that the conductive molecules, they start detaching from each other, so thereby allowing less current to go through it. So in perfect condition, when you have very low temperature, actually the freezing temperature is not favorable as well. Okay, but let's say you have a moderate temperature, it would almost act as a short circuit with a very low resistivity or low resistance, allowing more current to flow. When you have an overheating condition, this resistance starts increasing, meaning that the conductive material would start dilating, disconnecting more the current or resisting more against the current from flowing from one side to another. And this partial current blockage, okay, would be detected as a low current within the electronic board and interpreted by the computer as overheat. Okay, so this is why at times you could have also errors within the sensing resistance. So in case it snapped, it would indicate a wrong fire alarm, although there was no fire, but the resistance itself had snapped. Why? Due to the fact that in overheated conditions, the resistance would dilate too much so as to become like an open circuit. Failure modes: false fire warnings at first, as we mentioned before. When you have a heat detection resistor snapping off or breaking, it would emulate a fire within the engine or wherever it has been installed. I'm talking about the sensor. Loss of detection capability for whatever reason. So let's say the detection device should be wired or should be powered by a current, like the smoke detection system. Okay, if you had lost the power on that system, you would no longer be able to detect a potential fire by prematurely detecting a smoke first, or preemptively detecting the smoke and interpret it as a development of fire in the undercarriage or whatever the smoke detection system has been installed, and the sensor itself. Sensor contamination or damage, as we mentioned also before, that the smoke detector can confuse dust as being smoke. So if you have a contamination, it can signal a false alarm due to a blockage of the photodiode by the presence of dust, and it wouldn't be smoke. And finally, power supply failure, which supplies the detection systems. Once it's out, it can no longer work. They are out of service because we are relying on power in order to measure the output of these systems. Thermal detection principle. Thermal detectors trigger when temperature exceeds a threshold. So when the temperature becomes higher than or equal to the trigger temperature, that would trigger the alarm. That would be notified within the cockpit. Or when the rate of temperature rise exceeds a preset limit. So when the change of the temperature is so fast, okay, between one value to another. So this fast derivative, this fast differential, by the way, it's like a derivative. And if I want to plot it mathematically, it would be like a fast inflection. That would be interpreted as an abnormal event within an electronic board or wherever you had placed your sensor, because that sudden shift in temperature would indicate something like a sudden event occurring, a sudden overheating of the board or the engine, etc. Okay, so the change rate should be greater than or equal to the critical change rate of the temperature in a small lapse of time. That would be the trigger to the alarm in such case. Firefighting priorities and decision making. Effective fire management relies on prioritization, time awareness, and correct decision making under stress. So it relies again on prioritization, what should be done first, being time aware of the situation that's developing, so you need to be acting quickly, and correct decision making even under stressful conditions. Firefighting priorities: at first, protecting human life, control and suppress the fire by shutting down the engine, moving the engine thrust lever to idle, cutting off fuel, triggering the extinguisher, etc., and maintain aircraft control, which is very important. And finally, plan to divert to the nearest runway possible in order to execute an emergency landing. Time critical nature of fire. So the fire growth can be exponential in enclosed spaces. The heat release rate is equal to Q0, which is the initial heat release, multiplied by the exponential of KT, where T is the time, of course, and K is the fire growth constant. Delays in response significantly reduce survivability in such case. Decision-making considerations. First, location and severity of fire. So where did the fire start? Smoke density and toxicity within the cabin. Aircraft systems availability, because the fire, as it spreads, it will start to shut down different systems on board. And finally, nearest suitable airport for landing, for an emergency landing. The guiding principle is a fire on board is an emergency requiring immediate landing. Module or Chapter 12, Complex and Compound Emergencies. Complex and compound emergencies involve the simultaneous or sequential failure or multiple aircraft systems going down at the same time, often interacting in non-linear and unexpected ways. So it's not like one after the other sequentially. Multiple things can go down in a non-linear manner. These situations place extreme demands on crew workload, situational awareness to keep controlling and to maintain the controllability of the airplane, and decision making, and are a leading cause of loss of control and accident escalation. So, for instance, when you have multiple system failures, multiple system failures occur when two or more independent systems that are very critical to run the aircraft fail at the same time or within a short period. Common triggers: severe weather encounters, for example, for whatever reason, which can lead to icing conditions, for instance, loss of control. Multiple reasons here: fire or smoke events, okay, that can take down multiple instruments, multiple vital systems on board. Uncontained engine failures, which can shut down the entire power for the aircraft. Electrical bus or generator failures that can take down also multiple interconnected groups or systems within the same group due to the fact that they are being fed on power from the same electrical bus. And finally, structural damage, like the engine exploding in midair, tearing off on its way multiple hydraulic systems and other control systems, which, by the way, had happened in the past. Redundancy and common mode failure. Aircraft systems are designed with redundancy. However, common mode failures can defeat redundancy when multiple systems rely on the same components or shared components, like when you have multiple visualizers that are taking the reading, that are depending on the same readings of the same instrument. For example, the pitot-static system. Okay, so the probability of simultaneous independent failures is given by P total is equal to P1 times P2 times P3 for the probability of different systems going out at the same time, which would be a very small probability, but it can happen. Okay, for common mode failures, P total is approximately equal to the P of probability of common systems going down altogether at the same time. Why? Because they would be interdependent in such case, where a single event can cause multiple failures at the same time, which is different than when you have multiple systems that are independent going out simultaneously. Operational impact: degraded flight controls, that's one. Loss of navigation or communication, which is as bad almost, okay? Reduced situational awareness, for example, due to loss of crucial instruments such as the attitude indicator, VSI, altimeter, and increased crew workload in order to rectify the problem. By the way, the degraded flight controls would be caused by a hydraulic problem, okay? Hydraulic system failure, the actuator failure that converts from the hydraulic pressure into a mechanical pressure based on the system. If we're talking about a fly-by-wire system, that would be from the input of the pilot to, a generated, it would be driving the current into and converting it into a mechanical action against different flight controls or control surfaces. So it depends here, okay? But usually it would be due to a mechanical failure, like a rudder jamming or a hydraulic system failure, or other things like something within the transmission system, the mechanical or hydraulic transmission, from the pilot input all the way to the controls themselves. Cascading failures. Cascading failures occur when an initial failure triggers secondary and tertiary failures, often amplifying the severity of the problem and of the emergency. So you would have a failure propagation. A typical cascade may follow. So you would start with something like an initial fault, for example, an electrical short circuit. Then it would lead to something more serious like the system isolation or power loss. Then the loss of dependent systems that are relying on the same electrical line that has been shorted and then isolated, along with the other systems that are relying on that. And finally, it can lead to crew confusion and misdiagnosis of the problem. System dependency model. Let Fi represent the failure of system I, okay, indexed as I, whether I equal 1, 2, 3, etc. A cascading consequence may be modeled as F1 leading to F2, leading to F3, all the way. The probability of cascade increases with system coupling density, okay? How much are the system interdependent and coupled together, okay? Now, the human contribution, time pressure, and incomplete information increase the risk of incorrect decisions or actions that can further propagate the failure, making something that was originally bad even worse and augmenting the failure chain. Decision making under uncertainty. During compound emergencies, crews must take action or make decisions at first with incomplete, ambiguous data and information, or conflicting information being fed to them by erratic instruments. Okay, the sources of uncertainty would be inaccurate or failed indications on the screen, such as the ECAM or the ECAS or the PFD. Second, conflicting alerts. So you would have, we mentioned that before, a conflict between an overspeed indication and a stall warning, which cannot come together. Like they are 180 degrees opposite to each other. Okay, but usually the stall warning is way more accurate than the overspeed warning. Okay, that's for sure. Conflicting alerts, unknown system status. So you wouldn't know the current performance of the system. That would impair your judgment. And rapidly changing conditions. So when you have multiple problems escalating one after the other. And rapidly changing conditions. So this is when you have one problem leading to another, etc. Risk-based decision model. Expected risk R can be expressed as R is equal to the sum of the probability of an outcome for a decision or an action that had been taken multiplied by the consequence of that action, okay, or of that outcome in terms of severity. So R is equal to the sum of different probabilities for each outcome, and each outcome probability should be multiplied by the severity for that outcome, the severity consequence. Okay, you add that together, you would get the risk assessment for that action. So decisions should minimize total expected risk rather than optimize for a single parameter. So again, decisions should minimize total expected risk rather than optimize for a single object, for a single parameter. It should account for everything in a way as to make the overall actions together less risky on the aircraft and the flight. CRM or crew resource management. Effective CRM mitigates uncertainty through task sharing and load sharing between different crew members, cross-checking so as to confirm and validate different values that are being measured, different indications that are being checked, to have multiple, like, in the Bible it says, in the presence of the multitude of counselors, or in the multitudes of counsels, there is safety. The same principle applies here. When you have multiple people working diligently on the same task and sharing ideas and information and trying to assess the problem and troubleshoot, they would get to a fine conclusion and a fine decision making, which had happened before on Qantas flight, by the way. Third, explicit communication between different members and like one and task, task sharing. Again, this implies that one of the crew members, such as the pilot, would be flying the aircraft. The co-pilot would be observing and monitoring the airspeed, for instance. Okay? And use of standard operating procedures such as the checklist. Diversion planning during emergencies. Diversion planning becomes critical when normal flight continuation is no longer safe. The different criteria that usually are met in order to make the decision for a diversion and an emergency landing would be aircraft controllability, so a loss of rudder, of elevators, of the engines, okay? Fire or smoke presence, so fire or smoke on board, that would be definitely a decision maker to land the aircraft ASAP. Fuel endurance, so the fuel is running out. And weather and runway suitability. Fuel endurance estimation. The remaining flight time can be approximated by T is equal fuel remaining divided by the fuel flow rate. Okay, so fuel flow rate, of course, this is a time-based value. So usable fuel divided by fuel flow rate, it would give you the remaining flight time that you can still use in order to remain airborne. Distance to alternate, like maximum reachable distance D, would be given by D equal V ground velocity, or ground speed multiplied by time. This determines whether a diversion airport is reachable within safety margins. So to make it a little bit simpler, distance to alternate does not mean the alternator that generates an alternative current. This is not what we mean by that. So what we're talking about here is the distance reachable between the current position of the aircraft all the way to the closest runway. Okay, it should be at least equal to the ground speed multiplied by the time in which an aircraft can still fly on fuel without running out. Okay, or if it would run out of the fuel, how much glide can it go? Okay, how much with the gliding speed, the perfect or optimal gliding speed, can it still fly while in this situation being able or attempting to land on empty tanks? Okay, that would be an emergency landing in such case. So this determines whether a diversion airport is reachable within safety margin while fuel is still available in this case. Prioritization principle, the guideline or the guiding rule is land as soon as conditions permit at the nearest suitable airport. Case studies from real accidents and incidents. So for the selected case studies here, United Airlines Flight 232, 1989. Uncontained engine failure leading to loss of all hydraulics, successful partial control using differential thrust. This is what they did. Air France Flight 447, 2009. Sensor icing caused unreliable airspeed indications, leading to inappropriate crew responses and loss of control. Qantas Flight 32, this is, I believe, what I was mentioning here, 2010. Engine failure resulted in cascading system alerts. Disciplined systems management prevented catastrophe. Okay, because they had a full crew, the testing crew and the current crew, like the flight crew and the testing crew that test the pilot like cyclically every 6 months, I think. And Swiss Air Flight 111, 1998, electrical fire escalated into total aircraft loss due to delayed landing decision. Lessons learned: early problem recognition is critical. Avoid fixation on a single failure or problem. Maintain aircraft controllability at all times. Time is the most critical resource. Complex emergencies require crews to think systematically, prioritize survival over procedure completion, and make decisive choices under uncertainty and also under pressure. At the end, thank you so much for watching. God bless you. See you next time. I hope I can prepare something even more exciting next time. Let's see. No guarantees, no promises, so to speak. Okay, but hopefully we will get you something like this series, and I hope that you've enjoyed it already. And again, God bless you.